Hi, I'm Vladimir Podolsky, and today we are going to discuss basics of counting. Counting is one of the basic tasks in mathematics. And the main goal here is to tell how many objects are there of certain type without actually counting them one by one. Counting is used in many other parts of mathematics and in applications, so it's a very important area. And there are two applications that are important for us. The first one is counting number of steps of algorithms to estimate the running time of an algorithm. And the second one is counting probabilities. If you have seen our the first course of our specialization, What is a Proof, then you can note that we have already encountered counting twice there. First time when we tried to estimate the running time of some algorithms, and the second time when we tried to apply pigeonhole principle. To apply pigeonhole principle, we have to count the number of pigeons and the number of pigeonholes. But counting turns out to appear even in simple real life situations. Consider the following example of license plates. Suppose there is some country or state or region that introduces a new format of their license plates. And here is a Russian example. The new form of license plate, which was introduced about maybe 20-25 years ago, is the following. So there are 3 digits, 3 letters, and here 78 is a regional code. So for a fixed region, this code is fixed. So we have 10 options for digits from 0 to 9, and we have 12 options for letters, because these are Cyrillic letters, and they must look similar to Latin letters. So some Cyrillic letters, like those listed here, are not allowed. So how many possible license plates do we have with this format of a license plate? Is it enough for everyone? And what should we do in this situation if we are government so if we are introducing this license plate? Should we hire someone who will just list all possible license plates and count them one by one? Or should we do something smarter? So that's what we are going to discuss in this course. And in the end of this week, we will be able to answer these questions about license plates. So we will start with our most basic building block, rule of thumb. Suppose we have k objects of the first type and we have n objects of the second type. Then we have n plus k objects of one of the two types, of the first one or of the second one. So this rule is very simple. Here is a simple example. Suppose we are looking for a place to eat, and we have 7 options for the pizza place, and we have 5 options for a burger place. So in total then we have 7 plus 5 places to eat today. So that's the basic example. The rule is indeed very simple. Let's consider the following simple problem. Suppose we have a piece on a chessboard and it is positioned in the bottom left corner, and we need to move the piece to the position indicated on the picture. So, and in each move, the piece can move 1 step right or 1 step up. So how many moves do we need to get to the desired position? And if you have seen our first course, What is a Proof, then you can recall that we have encountered this problem there as well. Okay, let's see how we can get to this position. And there are several ways to do it. And for example, we can do it this way. So in this case, we need 8 moves. Okay, we can do it, for example, this way. We can move up first, then to the right, then up, then to the right again. And we need 8 moves again. We can do it this way. So we can go up, then right, then up, then right, then up again, and then right, then up again. So again, we need 8 moves. So in all cases, we needed 8 moves. We can try some other cases, and again, we will need 8 moves, because this is not a coincidence. So it turns out that we always need 8 moves. And here is the reason why. There are two types of moves. Moves to the right and moves up. So let's see. We would like to get to the third column of the board. So to get to the third column, moves up doesn't help us. So if we move up, we stay in the same column. And moves to the right helps us, and we need 3 moves to the right to get to the fourth column. It's fourth column. Okay, so now we need to get to the 6th row of the table, of the chessboard. So again, moves to the right now doesn't help. We stay in the same row. But moves up helps, and we need 5 moves up to get to the right row. So there are 2 types of moves. We need 3 moves of the first type. We need 5 moves of the second type. So in total, by the rule of thumb, we need 8 moves. So note that we are actually using the rule of thumb. It's very simple, but still we are using it in this argument. Okay, let's consider the next problem. Suppose we have integers from 1 to 10, and we would like to count how many of them are divisible by 2 or by 3. And okay, so this looks like a situation where we can apply rule of thumb, and let's try to do it. Let's see how many of integers are divisible by 2. And we can just list all of them. 2, 4, 6, 8, and 10. These are integers from 1 to 10, which are divisible by 2. Okay. So now let's see how many integers are divisible by 3. There are 3 of them, 3, 6, and 9. These are all integers that are divisible by 3 from 1 to 10. Okay, so now we can apply rule of thumb. There are 2 types of integers, and we can apply rule of thumb and get the result. There should be 8 integers from 1 to 10 that are divisible by 2 or divisible by 3. Okay, but let's check. 10 is a small number, so let's just count all these numbers directly. So let's see what happens. So here are all numbers from 1 to 10, and let's see how many of them satisfy our property. Okay, 2 is good, so 2 is divisible by 2. 3 is also good. 3 is divisible by 3. 4 is also good. 6 is also good. 5 is not good because it's not divisible by 2 or 3. 7 is not good. 8 is good. 9 is divisible by 3, and 10 is good. So now, if we count the number of green squares, we see that there are 7 of them. So the answer is actually 7. And so what happened? How it happened that our rule of thumb, a very simple and trivial rule, gave us the wrong answer. So actually the problem is with number 6. Note that if you look at the lists above, the list of numbers divisible by 2 and the list of numbers divisible by 3, number 6 occurs twice there. So when we summed up 5 and 3, we have counted 6 twice. And this is the problem. So we applied the rule of thumb in the wrong way, so we should not do it. And let's recall the rule of thumb, and let's see what actually we shouldn't do. Let's learn our lesson from this example. So let's recall rule of thumb. So we have k objects of the first type, there are n objects of the second type, and then we can say that there are n plus k objects of one of the 2 types. But now, an important remark. No objects should belong to both types, should belong to both classes in the rule of thumb. There should be disjoint. Objects of the first type should be different objects from objects of the second type. Then we can apply rule of thumb. Otherwise, it gives us wrong results, like in the previous example. So we have to be careful when applying rule of thumb. it is a good time to introduce a convenient language we will use, language of sets. Set is a very simple object. It's an arbitrary group of arbitrary elements, arbitrary objects. So we will denote sets by capital letters A, B, C, S, and so on. And sets can be given, for example, by listing all of their elements. Sets are given by their elements, and we can, to define some set, we can just give a list of elements. For example, this set consists of 4 elements, 0, 1, 2, 3. Okay, in this notation, the order doesn't matter. The order of elements in the set doesn't matter, so we can give the same set by the list 0, 1, 2, 3, and by the list 2, 0, 3, 1. It's the same set. And we allow repetitions in the list when we give a set in this way. So each element either belongs to the set or doesn't. So it cannot belong there twice. So the set 1, 0, 1, 3, 2, 3, the set of these elements is the same as just the set of elements 0, 1, 2, 3. So each element either belongs to the set or not. For us, sets provide a convenient language. In mathematics, sets are very important. They play a fundamental role. They are in foundation of mathematics. For us, sets can be just any list of any elements. For example, this is a set for us: 0, square root of 2, Isaac Newton, a leprechaun. This set consists of 4 elements. Here is the list of them. So this is a legitimate set for us. So in mathematics, it is known that there are pitfalls there. So you cannot just consider anything you want. For example, the construction like this, set consisting of all sets, it is a dangerous construction. You should be very careful with it. So, but we will not encounter these difficulties in this course, and we will not discuss them. We will not have this problem. So for us, set is arbitrary group of arbitrary elements. Okay, so a convenient way to view sets is by the means of Venn diagrams. So here is a Venn diagram for 2 sets, and here there are 2 sets A and B. Elements of A are depicted within the left circle. Elements of B are depicted within the right circle. So note that the circles are intersecting, and the intersection corresponds to elements that belongs to both sets. So if there are elements that are in both sets, they will be in the intersection of 2 circles. So suppose there are 2 sets, and here is a picture, and we would like to introduce a couple of operations over sets. First, the intersection of 2 sets. And the intersection of 2 sets is again a set, and is a set of all elements that belong to both A and B. Next operation is a union of 2 sets, and this is the set that consists of all elements that belong to either A or B. If you have seen our first course, What is a proof? Note that, recall that we had Boolean logic there, and operations and or on Boolean variables. And note that operations for intersection and union are similar in their looks to operations in Boolean logic. And recall also that we have Venn diagrams there as well. And the Venn diagram for AND operation looked like that, like for intersection, and the Venn diagram for OR operation looked like a Venn diagram for union. This is not a coincidence. There is a correspondence between Boolean operations and operations over sets. We will not discuss it in details, but there is a connection there. There is a correspondence. Okay. And the last definition we would like to introduce is the number of elements in the set, which is denoted like this. Note that the set can be infinite. For example, the set of all natural numbers. It is an infinite set. So this number, the number of elements in the set, can be infinite. It can also be 0. There is a set with no elements, a so-called empty set. So this is our last notation here. Okay, and now we can proceed to back to combinatorics. Okay, now we are going to generalize our rule of sum a little bit. But first, let's state the rule of sum in the language of sets. So in the language of sets, this rule sounds as follows. So suppose there is a set with k elements, and there is a set B with n elements, and what is important, this set do not have common elements. We have seen that this is important before. Then the set, the union of sets A and B contains n plus k elements. And here is a picture. There is a circle for A, there is a circle for B. They do not intersect, so there are no elements in the intersection. And so here is the set of all elements in the union of A and B. It is denoted by green color. So there are n plus k elements there. So here is a rule of sum. But what if sets A and B are intersecting? Okay, we cannot apply rule of sum now. But what if we still would like to count how many elements belong to one of the sets, A or B? What if we want to count the number of elements in the union of A and B? Okay, let's see what we can do. So we would like to count this, the number of elements here. Let's see what we can do. Okay, let's start with the rule of sum. We can just consider the number of elements in A plus the number of elements in B, as in just as in the rule of sum. And we know that the answer will be wrong if there is something in the intersection. Okay, let's see what we have done here. We have counted all elements of A, and then we have counted all elements of B. And why is this wrong? We have counted elements in the intersection twice. Note that the color there is a bit more intense, so it denotes that we have counted them twice. We have colored this area first when color in A and second when color in B. Okay, now we are wrong. We have a wrong number. But what we can do? Okay, we can just subtract what we have counted twice. If we counted it twice and now we subtract the number of elements there, then we will have the right answer. So that's what we can do. And the number of elements there is just the size of intersection of A and B. So this gives us the following results. The size of union of A and B is the size of A plus the size of B minus the size of intersection. So that's how we still can compute the number of elements in the union, even if the sets are intersecting. Note that the rule of sum is the special case of these equations when the size of intersection is zero. The intersection is an empty set. Okay, let's summarize what we have learned in this lesson. Counting starts with very simple things, just the rule of sum, and we can build everything else from it. But note that even these simple things can be tricky. A rule of sum, can be tricky. We have to be careful when we are applying it. And in the next lesson, we will see how we can build something more complicated, more involved from the basic building blocks. Hi, I'm Vladimir Podolsky, and today we are going to discuss recursive counting. Let's start with the following problem. Suppose there are several points which are connected by arrows, and points are represented by circles here. There is a starting point S, which is called source, and there is a final point T, which is usually called sink. How many different ways are there to get from S to T, following these arrows? Okay, let's try to consider this problem. There are several different paths here, and they look completely differently. And the main problem, if you try to do it by hand, is how not to miss anything when you just list all possible paths. And by the way, this is one of the advantages of using mathematics here. Mathematics comes with proof. So if you use some formula, then you know it is correct and you know you haven't missed something. If you try to count by hand, then you can miss something where you have a long list of paths and it is easy to not to notice something. So mathematics reduces the number of places where you can make a mistake. Okay, so what can we do with this problem? Okay, we can count this this number of paths recursively. For each node, we will count how many paths do we have from to this node from S, and we do it for all nodes one by one. And on our way, we will use the rule of sum. Let's note it. So here we will use our basic building block, the rule of sum. Okay, we will start with the simplest possible node, S. So there is exactly one way to get from S to S. Just do nothing, just stay there. And so the answer is 1. Okay, let's consider the next node. This one. There is only one way to get to this node. There is only one arrow incoming to this node, and it goes from S. So there is one way to get to S, and so there is one way to get here. Here, there is one way to. There is only one arrow which goes into this node. So again, there is only one way to get here from S. Okay, now we get to something more interesting. There are two possible ways to get to this node. So we can go here from above and from below. And in both cases, there are one possible way to get to the corresponding node, so to the node on the top and the node to the bottom. On the bottom. So we have to sum up ways of two type, which go through the vertex above and the paths that go through the vertex below. So we apply a rule of sum, and 1 plus 1 is 2. Okay, let's proceed to the next node. Again, for this node, we have two ways to get here. There are paths of two types. The one which goes from the node which is labeled by 1 currently, and the other which goes through the node which is labeled by 2. So there are two types of paths here, and there is exactly one path of the first type, and there are two ways to get to the node in the middle. So there is one path of the first type, and there are two paths of the second type. So we have to add this up by the rule of sum, and we get 3. Now this node is simple. There is only one edge going here, and there is only one path to get to the previous vertex, to the previous node. So there is only one way to get here. Okay, and now the final node. There are 3 edges which go into T, and so there are 3 types of paths. There are three types of paths by which we can get to T. The one which gets to T from above, the one which gets to T from the middle, and the one which gets to T from below. And there are 3 paths to. There are 3 ways to get to the vertex above. So there are 3 paths of the first type, there are 2 paths of the second type, and there is 1 path of the third type. So we sum this up by the rule of sum, and we get 6. Now let's proceed to our second basic rule of counting, rule of product. Suppose there are k objects of the first type and there are n objects of the second type. Then there are k times n pairs of objects, where the first object is of the first type and the second object is of the second type. Here is a simple example. Suppose you got to some place to eat, and there are 4 options for pizza in menu, and there are 3 options for soda. Then you can pick a pair consisting of a pizza and a soda in 4 times 3 ways. So there are 12 possible ways to pick your menu. And just for clarity, let's just draw the picture of all of these options here in this table. Columns correspond to pizzas, and rows correspond to sodas, and in each cell we have the corresponding pair of soda and pizza. So here are 12 options. Let's state the rule of product in the set language. So there is a finite set A and there is a finite set B. This means that both sets has finitely many elements. Then there are A times B, meaning the number of elements in A times the number of elements in B, of pairs of objects, there the first object in the pair is from A and the second object in the pair is from B. Okay, let's get some intuition why the rule of product is true. It also looks rather simple, but still, let's see. Suppose we have the set A with elements A1 and so on AK, and there's a set B, B1 and so on Bn. And let's draw the same table we have drawn in our previous example. Let's enumerate all columns by elements of B, and let's enumerate all rows by elements of A. So we have n columns and k rows. And in each cell of the table, in cell on the intersection of the row EI and the column J, we place the pair AI and BJ. And then note that the number of all pairs is the same as the number of cells in this table. And how can we count the number of cells in the table? We can just multiply the number of columns by the number of rows. So the number of pairs is the same as the number of cells in the table. So to count the number of pairs is the same as to count the number of cells in the table. So that's why the rule of product is true. In the beginning of this lesson, we discussed how we can count the number of paths in the picture with nodes and arrows recursively. Let's try to look at the rule of product from this point of view. So here is the rule of product. And let's see whether we can express this rule in terms of counting paths in some picture with nodes and arrows. Okay, so here is the rule of product, and let's consider the following example, just for simplicity of the presentation. It doesn't matter really, but just let's fix some numbers. Suppose the size of A, the number of elements in A is 5, and the number of elements in B is 3. And let's consider the following picture. We have 3 nodes, S, T, and the node in the middle. There are five arrows going from S to the middle node, and there are 3 arrows going from the middle node to T. Okay, and let's count how many nodes that five arrows corresponds to the size of A and 3 arrows corresponds to the size of B. And now let's count how many paths do we have in this picture. There is only one way to get from S to S, which just stay where we are. There are 5 ways to get from S to the middle node. We can pick one of the 5 arrows from S to the middle node. And okay, if you recall how we did it before, so we have to apply rule of sum. There are 5 types of paths, 1 path of each type, so we add 1 to itself 5 times and we obtain the result 5. Now let's proceed to the node T. There are 3 edges going to T, so there are 3 types of paths that goes to T. 1 for each edge going to T. And there are 5 ways to get to the middle node, so there are 5 paths of each type. So we add 5 plus 5 plus 5, which is 3 times 5, which is 15. So we have 15 ways to get from S to T. And okay, and this corresponds to the rule of product. Indeed, if you look at this path, what does it do? Let's recall our example. A is the choices of pizzas, say pizza, and B is the set B are our options for soda. So each path from S to T consists of 2 steps. And on the first step, we pick an edge from A, and this means that we pick our option for pizza. And on the second step, we pick one of the edges corresponding to elements of B. So here we pick our choice of soda. So this path exactly corresponds to pairs of where the first element is from A and the second is from B. This path corresponds to pairs of elements and A and B. And so this picture exactly represents the rule of product. In particular, we see that to to show the rule of product, all we need is the rule of sum. That's exactly that's the only thing that we use when we count the number of paths in this picture. Hi, I'm Vladimir Podolsky, and today we are going to discuss how to compute tuples and permutations. Let's start with tuples, and let's consider the following problem. How many different 5-symbol passwords can we create if we can use only lowercase Latin letters? And so the size of the alphabet is 26. So how many passwords are there? And it turns out that to solve this problem we need only the rule of sum, and that's it. But we need to solve this problem step by step, and we should apply the rule of sum step by step. So let's see how to do it. And let's start with not 5-letter password, but just with 1-letter password. Then clearly there are 26 options for 1 letter, and so there are 26 possible passwords of 1 letter. So this is not much. Okay, let's proceed to 2 letters. Now we have 2 letters, and we have 26 options to pick each of them. And this is exactly the setting for the rule of sum. We need to pick the pair of objects. The first one we can pick in 26 ways, and the second one we can pick in 26 ways as well. So the rule of product tells us that there are 26 times 26 pairs. This is 676. Okay. Let's proceed to 3rd letters now. And what we have already know from the previous calculations is that we can pick the first 2 letters in 676 ways. Okay, now we can pick the 3rd letter in 26 ways. So we can apply the rule of product again. Now the element of the first set is already the pair of the first 2 letters, and the element of the second set is the 3rd letter. So we have to multiply the number of elements in the first set, the number of elements in the second set, so we multiply 676 times 26, and here is the answer. That's already something. Again, not a lot, there are not many passwords of 3 letters, but already we have some considerable number. Okay. Let's proceed further, and we can just argue by the same way. We now know that the number of passwords, the number of sequences of 3 letters, we have already calculated the number of sequences of 3 letters. It is 26 times 26 times 26. We can pick the 4th letter in 26 ways. So now we can pick, so we can apply rule of sum again. The element of the first set is a triple of first 3 letters, and the element of the second set is the 4th letter. So now for 4 letters we have 26 times 26 times 26 times 26 possible passwords. And we make this step again. So for 5 letters we now have 26 multiplied by itself 5 times. And this is this number. So this is how many passwords we need so we have, if we are only allowed 5 letters, and we can only use lowercase Latin letters. Okay, so we have shown these arguments on some specific example, but this is a general argument. Suppose now we have the following setting. Suppose we have a set of n symbols, so we choose from n symbols now. And we ask the following question: how many different sequences of length k we can form out of these n symbols? So n and k are parameters. Here they can be anything. These sequences are usually called tuples, and this is the first standard setting we have to consider in Combinatorics. This is an important setting, and we will use it later on. Okay, so let's see. We can just apply the same argument. Just instead of 26 for n and 5 for k, we can now have arbitrary parameters. let's quickly go through this argument again. There are n possibilities to pick the first letter, and for each next letter there are again n possibilities. So we apply the rule of product repeatedly, and each time we multiply by n. So in the end, the answer is the product of n by itself, k times, that is n to the k. So this is the answer in general form. So this is the answer in this standard setting of computing tuples. Now we are ready to get back to our motivating example from the beginning of this lecture. Consider Russian license plates. There are 3 digits there, there are 3 letters, and 78 here is a regional code. So we have 10 options for each digit, from 0 to 9. We have 12 options for letters. This is because we can use only those Cyrillic letters that are similar to some Latin letters. And now, how many plates do we have for a certain region? How many possible plates do we have? Okay, let's see. For each digit we have 10 options. So now we have to pick a tuple of 3 digits, and it can be chosen by the previous result, by the previous statement. It can be chosen by 10 times 10 times 10 by 1000 possible ways. Okay, next we have to pick 3 letters, and each letter can be chosen in 12 ways. So we have a tuple of 3 letters, and it can be chosen by 12 times 12 times 12, which is 1728 possible ways. Okay, now how many ways do we have to choose a sequence of digits and a sequence of letters? Again, we can apply a rule of product. We have to choose a tuple of length 3 of digits and a tuple of letters of also length 3. We have to multiply these two numbers, and so in total we have 1,728,000 license plates for a region. Okay, so we have done the calculations. We do not need anyone to list all of the license plates. Here is the answer. We have done this in just 2 slides. Okay, is it enough? So we have this number of license plates. Is it enough? It turns out it's not. For example, if we look at Moscow, it's one of the regions, we have more than 5 million vehicles in Moscow as of 2016. Now it's in 2017 it's even more. So it's not enough. Okay, does it mean that by pigeonhole principle, so vehicles here are pigeons and license plates are pigeonholes? Recall that we have a pigeonhole principle. If there are more pigeons than pigeonholes, then there should be at least 2 pigeons in one pigeonhole. So does it mean that there are 2 vehicles with identical license plates? No, it doesn't. So the solution was that there were several regional codes introduced for the same region. But still, this required introduction of not 2-digit regional code like on the picture 78, or instead we had to introduce 3. So now we have 3-digit regional codes as well. So we have seen that the rule of product allows us to compute the number of tuples of a certain length over a certain size, with a certain size of alphabet. So, but this rule can give us much more. In the next example, we will see how it allows us to compute the number of tuples with certain additional restrictions. Consider the following problem. Consider integers below 10,000 and above or equal to 0. That has exactly 1-digit 7. So how many integers with this restriction do we have? Okay, So first of all, let's note that we can represent the integers of this form by a sequence of digits of length 4. Why of length 4? So note that numbers below 10,000 can be represented with length 4, but there are also numbers with 3 digits. How can we represent them by a sequence of digits of length 4? Note that this is easy. They just correspond to sequences starting with 0. So indeed there is a correspondence between numbers below 10,000 and sequences of digits of length 4. Okay, so now we need to compute sequences of digits of length 4 that has exactly one digit 7. Okay, so let's start with this unique digit 7. We can place it to any of 4 positions. So there are 4 cases. We can place it to the first position, to the second one, to the third one, and to the fourth one. And if we compute the number of sequences of length 4, the number of tuples of length 4 in all 4 cases, then we can sum these numbers up and get the answer just by the rule of sum. Okay, so let's do it. Let's consider one of the examples. So let's place 7, for example, on the second position. Okay, how many tuples do we have with 7 in the second position? Note that we can pick each other digit in 9 ways. Why? Because 7 is forbidden. There is exactly one 7 in this sequence. So 7 is already there. So for other positions, 7 is forbidden. So it leaves us with 9 options. Okay, so now we need to pick a tuple of length 3, where each digit can be picked from 9 options. So we apply our previous result, and we can say that there are 9 times 9 times 9. This is 729 sequences in this case. And note that this argument doesn't matter that 7 is in the second position. It's the same if it is in the first position, the third, or in the fourth. The answer is the same no matter where we put digit 7. So in all cases, in each of 4 cases, we have 729 sequences. Okay, so there are 4 cases where we have 729 sequences in each of them. No sequence can occur in 2 different cases, because sequences in 2 different cases has number 7 on different positions. So we can safely apply rule of sum. We sum up elements of sets, and there is no element in the intersection of any sets. So we can safely apply rule of sum, and so the number of sequences in all 4 cases is 4 times 729, which is 2916. So there are these many numbers below 10,000 with exactly one digit 7. Okay, is it a lot or not? So we can see that. So in total we have 10,000 numbers below 10,000. Note that 0 is also, we are also considering 0. So the fraction of numbers with exactly 1/7 is 2916 divided by 10,000. This is below 1/3, but above 1/4. So this is somewhere in between. These are rough estimations. And these estimations give us, note that these estimations give us the following. This is the probability. So we have, this is an estimation for the probability to get exactly one digit 7 if we pick a number below 10,000 randomly. So we have discussed how to count a number of tuples, and now we can move on to our next standard combinatorial setting, our second standard combinatorial setting, permutations. We will count how many permutations are there. Okay, so consider the following general problem. Suppose we have a set of n symbols, and we would like to count how many different sequences of length k are there, consisting of these n symbols, but with additional restriction. We are not allowing to to use the same symbol twice. Okay, so tuples of length k without repetitions of letters are called k permutations. And that's what we are going to compute in this problem, the number of k permutations we are going to compute in this problem. And let's make the following observation, useful observation. If n is less than k, if the number of symbols in our disposition is less than the length of sequence we are trying to construct, and we are not allowed to repeat letters, then the answer is simple. There are just no permutations there. There are just not enough different letters to construct a sequence of length k. So in this case the answer is 0, and this case is simple. So let's further on assume that k is at most n, and let's consider this case, the non-trivial case. So let's proceed to the solution to our problem. Okay, so so here we see our sequence. We denote the symbols by stars. Let's enumerate them from 1 to k. And we will apply the rule of product. So we will solve this problem using the rule of product. So the first symbol we can pick in n ways. So what about the second symbol? How many choices do we have there? And note that we can place there anything except the symbol we already placed in the first position. So there are n-1 options for the second symbol. The symbol in the first position might be any symbol, but for any symbol in the first position there are n-1 possibilities for the second symbol. So there are n possibilities for the first symbol. For each of them there are n-1 possibilities for the second symbol. So in total we have n times n-1 possibilities to pick the first and the second symbol. Okay, and now we can proceed in the same way. Consider the first symbol. We can pick the first two symbols by n times n-1 ways, and for the third symbol, whatever the first and the second symbols are, for the third symbol we have n-1 options, all symbols except the symbol in the first position and the symbol in the second position. So there are n-2 possibilities for all ways to pick the first and the second symbol. So for the first three symbols we have n times n-1 times n-2 possibilities, and so on. For each next symbol we have one less option, and in the end, so for the last symbol we will have n-k+1 option. So this might require a moment's reflection why it's n-k+1 and not n-k. One easy way to observe it is to look at, so let's see, if near the first symbol we have one number above and one number below, 1 and n. For the second symbol it's the same, we have two numbers, 2 and n-1. Note that for each symbol, for the first, for the second, for the third and so on, the sum of these numbers is n+1. And when we move to the right, the first number increases, the second number decreases. So the sum of these numbers always stay to be equal to n+1. So in the end, it also should be equal to n+1. So it should be n-k+1 below there. So that's the easy way to observe that this is n-k+1. There are n-k+1 options there for the last symbol. Okay, so in total we have, now we have to multiply all of these options, and so we have n times n-1 and so on times n-k+1 k permutations of symbols of length n. Okay, so this is not a very nice looking formula. So there is a convenient notation to make it look more simple and more short. A convenient notation is n factorial. So by n factorial is just the product of numbers from 1 to n. 1 times 2 and so on times n. And in this notation, the number of k permutations of n symbols looks nicer. It is, note that we have product of, the answer to our problem was the product of all numbers. We multiply n by n-1 by n-2 and so on, but we stop on n-k+1, so we can write it as n factorial divided by n-k factorial. So we consider n factorial and we divide it by all multipliers we do not want in our product. So the answer in these terms is n factorial divided by n-k factorial. And okay, one important observation to make. And what if n minus k is equal to 0? This is possible. So what if n is equal to k? Then this formula it looks like we try to divide by 0. N minus k is 0, so we try to divide something. Is this an attempt to divide by 0? No, it's not. It's an attempt to divide by 0 factorial. And we haven't said what it is yet. And the standard convention here to make this formula true only also for this case, the standard convention is to say that 0 factorial is 1. So that's what we will agree upon, and then this formula works also for the case of n equals k. So, and we are done. The answer to this problem is n factorial divided by n minus k factorial. So now let's consider the following specific example. So we have n books, n different books, and we would like to place them on the shelf in some order. So how many different orders, in how many different orders we can do it? Okay, we can think of each book as a symbol. And now what we need to do, we need to count how many sequences of n symbols do we have. And again, as in the previous problem, we are not allowed to repeat the symbol twice. We cannot place the same book in two places simultaneously on the bookshelf. So we need to count n permutations of n symbols. And these are called just permutations. If we have n permutations of n symbols, then we can just omit the prefix n there and talk about just permutations. This is a very standard object in combinatorics. And by the previous result, we have n factorial of them. So we have shown, our previous problem shows that there are n factorial of such permutations. And so there are n factorial ways to place n books on the shelf. There are n factorial orders to place n books on the shelf. And recall, so if you have seen our first course, What is a Proof, recall that we have used this formula when discussing magic squares. Okay, so in this week we have started the discussion of combinatorics. This field is important and will be important for us. It is important for probability theory. It will be important for estimation of running time of algorithms. And it is also important in mathematics in general. And we have already discussed two standard settings in combinatorics, tuples and permutations. We have discussed how we can compute how many tuples are there of certain length over certain alphabet and how many permutations are there of certain length over certain alphabet. And these two settings already help us in many settings. We also have discussed recursive counting. It is also useful, especially if we are trying to compute something, not to produce a formula, but to compute something by an algorithm. Recursive counting is very useful there. But we still do not know everything we need. For example, if we would like to count what are our chances to get 2 aces in the card game if we have 6-card hand, we still do not know how to do it, and we will discuss this later on.
Hi everybody, welcome back to the next module of the Combinatorics course. In this module we are going to still discuss questions of the form how many objects are there satisfying some particular properties. We will see many interesting questions, and more importantly we will see solutions to such questions, and in many cases we are going to complement these solutions, with simple Python script. Okay, so before going into the details, let's first review what we've learned already in the previous module. So the first one is the rule of thumb. So if we have n objects of first type and k objects of the second type, and these two sets of objects do not intersect, meaning that they do not share any common object, then there are exactly n plus k ways of selecting some object out of these two groups. Okay, so to give an example, consider these two sets or two lists. So the first list is A, it consists of Alice, Bob and Charlie, and the second list is B, and it consists of 4 digits, 0, 1, 2 and 3. Then if you compute the sum of these two lists, then it will contain all these elements, and of course it has length 7, right, as expected. The next one is the rule of product, and it says that if you have n objects on one hand and k objects on the other hand, and you would like to select a pair of two objects, one of the first type and one of the second type, then the number of ways of doing this is equal to n times k. Once again, let's check this with Python on some small example. So assume that we have a list A consisting of just 2 letters A and B, and also we have a list B consisting of 3 digits, 1, 2 and 3. Then the number of ways of forming a pair of an object from the list A and an object from the list B is equal to 6. That is to the product of the length of A and the length of B. All such possible pairs are shown here on the slide. So you can either take A or B, so these are 2 choices, and then you can, as a second element, you can either take 1, 2 or 3, so 3 choices. So the number of ways is 2 times 3. Okay, so the next important object is tuples. So the number of way of, if you have n objects and you would like to organize, you would like to form a tuple consisting of, or you would like to form a word consisting of k elements such that you allow repetitions, that is, at any position there can be any of your n elements, then the number of way of doing so is n to the k. Once again, let's show an example. Assume that we have 2 letters A and B, and we would like to construct all possible sequences of length 4 that consist of letters A and B. Then the number of ways of doing so is equal to 2 to the power of 4, right? And indeed, so for any of 4 positions, you have 2 choices, right? You either take A or you take B. So by the product rule, the number of ways of doing so is 2 times 2 times 2 times 2, which is nothing else as 2 to the 4, right? And all such positions are shown here on the slide. So the first such possibility is A, and then the last one is B, and you can generate all such tuples using the product method of the itertools library. Okay, so finally let's discuss k permutations. In this case, what you would like to do is to, given n elements, you would like to organize a word, given n letters, you would like to form a word of length n such that there are no repeated elements in this word. Okay, in other words, you would like to construct a k permutation. Okay, so in this case, for the first position you have n choices because you can select any of n elements. For the second position you have n minus 1 choices. I mean all the remaining elements except for the first one. For the third position you have n minus 2 choices, and so on. So by the product rule, once again, the total number of ways of doing so is n times n minus 1 times n minus 2 times, and so on, n minus k plus 1. And it is convenient to write this product as follows. It is n factorial divided by n minus k factorial. As usual, let's try to generate all such k permutations. We are going to do this with the method called permutations, and assume that we have 5 letters A, B, C, D, E, and we are going to generate all permutations of size 2. So for the first position we have 5 choices. For the second position we have 4 choices, so the number of ways of doing so is equal to 20. Let's check it, and indeed the following code produces us all 20 such 2 permutations. So it all starts with A, B, and it all ends with E, D. Let's now count the number of games in a tournament. More precisely, the setting is the following. We have 5 sport teams, and they played a tournament, meaning that each team played with each other. So the question is, what was the number of games in this tournament? So visually it looks as follows. There are 5 teams, A, B, C, D, and E, and every 2 of them are connected by a segment, meaning that they played a game. And basically our goal is just to compute the number of segments. This is essentially a toy problem, but what we're going to do is to design a general formula not for 5 teams, but for any number of teams. Okay, so let's start to count. What we know is that there are 5 teams. So if we select any of them, then we know that each team played exactly 4 games, right? Why is that? Well, just because if a team is fixed, then there are 4 teams remaining, and we know that this team played with every of these 4 teams, right? Which means that by the product rule, what we know is that there are 5 teams and each of them played 4 games, which gives us 20 games. But there is actually a flaw in this argument, so let's try to catch it and let's try to fix it. Okay, so first of all, let's decrease the number of teams. So imagine if we had just 3 teams, so what would happen? Our argument actually gives that there are 6 games. Why is that? Well, there are 3 teams and each of them played two games with each of the remaining two teams. So the number of games is 6, but this is not correct, of course, which can be just easily seen by considering this simple picture. So we have 3 teams, there is a segment between any of them, and the number of segments is 3 instead of 6, right? To understand where is the flaw, let's just draw all possible games. Okay, so we have 5 teams, A, B, C, D, and E. So in the first row, we have all the games played by the team A. So it played indeed with AB, with AC, with AD, and AE. Makes sense, right? So for the second row, lists all the games played by the team B. It played with A, with C, with D, and with E. So still, it for some reason gives us 20 games in total. To understand what went wrong, let's try to rearrange all these games as follows. So we still have 2 rows and 10 columns, so there are still 20 games. At the same time, in this table, it can be easily seen that each game is actually counted twice. So we see that we counted the game between the teams A and B as AB and BA, and this happened actually with every game. For example, the game between B and C was counted as BC and CB. So this was our overestimation. So each game was counted exactly twice, which means that we actually need to divide our resulting count by 2, which finally gives us a correct result. It is 10. Okay, so and there is an important message for us. When we count something, we need to make sure that each object was counted exactly once. But if it turned out, as in our example, that we for some reason counted each object exactly k times, then it is easy to get the correct result. What we need to do is just to divide by k. So in our case, we counted each game 2 times. So what need to be done is to divide everything by 2. Okay. Now let's generalize it to arbitrary number of teams. The theorem here on the slide states that if we have n teams, then the number of games in a tournament where each game plays with each other exactly once is equal to n times n minus 1 divided by 2. Okay, let's prove it. So there are n teams, each of them plays exactly n minus 1 games, because there are exactly n minus 1 teams remaining. Okay, so the total number of games is n times n minus 1, but at the same time each game is counted twice, because if a game involves teams I and J, then it was counted twice. First, when we fixed the team I, and then it was playing with the team J, and on the other hand it was also counted when we fixed the team J, and then we counted the game as Ji. Okay, so we need to compute the product of n and n minus 1 and then divide it by 2. This is the resulting number. Okay, let's also complement this with a recursive proof of the same formula. Okay, so for this, let's denote by T of n the number of games in a tournament with n teams. Okay, then to get a recurrence relation for T of n, let's do the following. Let's split all the games into two parts. On one hand, we have all teams involving the first team. Okay, so there are exactly n minus 1 such games. Why is that? Well, because the first team played exactly n minus 1 games. We know this already. On the other hand, we have all the remaining games, that is, all the games that do not involve the first team. But this is the same as just all the games played by all the remaining teams. But this is nothing else as T of n minus 1, right? So just by definition, we need to count all the games played by the teams 2, 3, and so on n. So there are n minus 1 such teams. So, and we know that by definition T of n minus 1 is exactly this number, is exactly the number of games played by n minus 1 teams. This gives us the following recurrence relation. T of n is equal to n minus 1 plus T of n minus 1. So now we need to somehow get a formula for T of n from this recurrence relation. Okay? And for this we are going to apply the method, the so-called method of unwinding. Namely, let's first write our formula. T of n is equal to n minus 1 plus T of n minus 1. But then we can apply the same formula for T of n minus 1. So we leave n minus 1, but for T of n minus 1 we rewrite it as n minus 2 plus T of n minus 2. So we apply the same formula. This gives us n minus 2 plus T of n minus 2. Okay? But then we do the same with T of n minus 2. Okay, this gives us n minus 3 plus T of n minus 3, and so on. So we keep repeating this until we reach T of 1 or T of 0, which is in any case equal to 0, right? Because if we have 0 teams or if we have 1 team, then the number of games is in any case equal to 0. What remains is n minus 1 plus n minus 2 plus and so on plus 2 plus 1 plus 0. This is the so-called arithmetic series. Okay, let me remind you how to compute the sum of such series. A simple but useful trick to remember here is the following. If you write all the terms in your arithmetic series and then you write this series once again but in the reversed order, then what is convenient is that in every column the sum is going to be the same, and it is going to equal to just n, which means that it is very easy to compute the sum of all the numbers shown here on the slide. So we have n minus 1 columns, right? And in each column the sum is equal to n, which means that the sum of all these numbers is equal to n times n minus 1. At the same time, to get the sum for arithmetic series, we need to remember that we counted it twice here, right? So this is our original series and it is the reversed original series. So the sum in these two guys are the same, of course, which finally means that for the arithmetic series, the sum is equal to n times n minus 1 divided by 2. And this also is the answer for T of n. So this is another proof of the same formula. The number of games in the tournament is equal to n times n minus 1 divided by 2. Okay? So finally, let me complement it as usual with a simple script in Python. So for this, what we're going to do here is to take 8 teams, A, B, C, D, E, F, G, H. So there are 8 teams, and we are going to, using the combinations method, we're going to generate all possible games between these 8 teams. So what we expect to get is n is equal to 8 in this case. So the formula gives us 8 times 7 divided by 2, which is just 7 by 4, which is nothing else as 28, right? So let's run this script, and indeed it produces all possible 28 such games. So the length of each list here is 4, and there are 4 lists. Okay. Okay, and finally, let's do the following. Let's also show that our recurrent formula also produces exactly the same result. Namely, this was, as you remember, when T of n was defined to satisfy, T of n was defined to be the number of games in a tournament with n teams, and we proved that it satisfies the following formula. It is equal to n minus 1 plus T of n minus 1. And this allows us to just implement the following recursive procedure with the following base case. When n is at most 1, we just return 0 immediately. So if we then implement this procedure and task it to compute T of A, then the output is going to be, as expected, 28, which justifies our previous formula. We are now ready to introduce an important combinatorial object called a combination. So imagine that you are going to a car journey and you have 5 friends, but unfortunately you have only 3 vacant places in your car. So what you would like to compute is the number of ways of selecting 3 of your friends out of 5 that you are going to take with you to your journey out of 5 of your friends. Okay? Of course, in this case, we don't care who of your 3 friends is going to sit where in the car. So basically, what we're looking for, speaking more formally, is what is the number of ways of selecting 3 elements out of 5 elements. Okay? So let's try to compute this number of ways. So you need to select 3 friends. There are 5 choices of the first friend, 4 choices of the second friend, and 3 choices of the third friend, right? So this gives us 5 times 4 times 3. But as we've seen already, this actually computes not the number of subsets of 3 friends, but the number of 3 permutations, right? In particular, each subset, for example, of friends A, B, C was counted 6 times. It was counted as ABC, for example, as ACB, as BAC, BCA, CAB, and CBA. But since we are not interested in the actual arrangement of these 3 elements, we need to divide everything by 6, right? So we would like to count each subset exactly once, while it, in our current estimate, it was counted exactly 6 times. So the final answer is 5 times 4 times 3 divided by 3 factorial, which gives us 10. So this is an important combinatorial quantity. Let's also justify our count just by trying to generate all such combinations. Namely, here we have 5 friends A, B, C, D, E, and we ask the combinations method to compute all possible subsets of size 3 of all these 5 letters. So what it gives us is exactly 10 such possibilities. Okay? Now we are ready to give a definition. So if we have a set S, then its K combination is its subset of size K. Okay? So, and the number of different such subsets of size K is denoted by n choose K. So, where n is the size of the set S. So, more precisely or more formally, n choose K is defined to be the number of different subsets of size K of an n element set. And once again, it is pronounced as n choose K, and it is written like this. Okay, so this is a very important combinatorial quantity. So in particular, you can go to Google and compute any such number. For example, if you compute 5 choose 3 in Google, it will give you a result. Okay, once again, it is 10. So there are 10 ways of choosing 3 of your friends out of 5 your friends. Okay, now Before giving a formula, let's look once again at the difference between the number of 3 combinations and 3 permutations. So let's list all possible 3 permutations. So recall that in a 3 permutation, we just would like to put one of your 5 friends to the first place, then one of the remaining 4 friends to the second place, and then one of the remaining 3 friends to the third place. So this gives us 5 times 4 times 3, which is 60. And all 60 permutations, 3 permutations, are shown here on the slide. And they are arranged in a nice way, such that, as you see in the same column, we have exactly the same 3 elements permuted, right? And we know that for elements A, B, C, there are exactly 3 factorial possible ways of permute them, right? So, which means that the number of 3 permutations is 3 factorial larger than the number of 3 combinations. More precisely, what we see here is that in this table, the height of this table is 3 factorial, while the width of this table is 5 choose 3. At the same time, the total size of the elements in this table is the number of 3 permutations. And we know how to compute it. The number of 3 permutations is 5 times 4 times 3, which is nothing else as 5 factorial divided by 2 factorial, which is just 5 minus 3 factorial. So this gives us the following formula. The number of elements is equal to the height of this table times the width of this table. Okay? And this will lead us, this observation will lead us to the general formula for computing n choose k. So the formula is as follows. N choose k is equal to n factorial divided by k factorial and divided by n minus k factorial. Okay, so this is a formula, and now let's try to prove it. So we have actually everything needed to prove it already. Okay, so first let me remind you that n choose k is the number of subsets of size k out of n elements. Okay. Now, first, let's count the number of k permutations. Okay, so for k permutations, there are exactly n choices for the first element. Then there are n minus 1 choices for the second element, n minus 2 choices for the third element, and so on, n minus k plus 1 choices for the kth element. And this computes the number of k permutations, and we know already that it is equal to n factorial divided by n minus k factorial, which is just a convenient way of writing the expression n times n minus 1 times n minus 2 times n minus k plus 1. Okay, and this is, as we've discussed already, this computes the number of k permutations, but not the number of k subsets. And the number of k permutations is exactly k factorial times larger than the number of k subsets, right? Why is that? Well, because just when we count the number of k permutations, every subset is counted exactly k factorial times. Because if you have a subset of size k, there are k factorial ways of permuting its elements, right? Which finally gives us the estimate n factorial divided by n minus k factorial. Let me remind you that this part, n factorial divided by n minus k factorial, is exactly the number of k permutations, and we need to divide it by k factorial to finally get the number of different k subsets. Okay, so once again, let me show you the resulting estimate. So n choose k is equal to n factorial divided by k factorial divided by n minus k factorial. Hi everybody, welcome back. In this video we are going to consider an elegant combinatorial structure called Pascal's triangle. Let's start with the following well-known question. I mean, we have n students and we would like to form a sport team out of them consisting of exactly k students. So what is the number or way of selecting such a team? So the answer is n choose k. Well, why is that? Well, this is just because we are selecting k students out of n students. So just by definition, this number is equal to n choose k. Okay. At the same time, let's view at this number from a different viewpoint. Let's just fix some of the students and call her Alice. Then all the possibilities are divided into two parts naturally. First of all, there are teams with Alice. So first consider all the teams that involve Alice. I claim that the number of such teams is equal to n-1, choose k-1. Well, why is that? Because we already decided that Alice is in the team. Okay? This means that we still need to select the remaining k-1 students, and we need to select them from the remaining n-1 students. And this number of ways is exactly equal to n-1 choose k-1. Okay? So once again, the number of teams with Alice is n-1 choose k-1. Okay, now let's consider all other teams. There's teams without Alice. So we already decided that Alice is not going to be in the team. This means that we actually need to select the whole team, the whole k students from the n-1 students, everyone except for Alice, right? And again, just by definition, the number of such ways is n-1 choose k. And this gives us finally the following nice combinatorial property of the number of combinations. N choose k is equal to n-1 choose k-1 plus n-1 choose k. So once again, let me try to repeat this formula. This is the number of ways of forming a team, okay, of k students out of n students. And we represented this as naturally as two disjoint parts. So first of all, this is the number of ways of forming a team with some fixed student, which we called Alice, and this is the number of ways of forming a team without this student. So clearly the number of ways of forming a team is equal to the sum of these two numbers, because this is just all the possibilities. Okay, and this is an important property of these numbers. And there is an elegant way of visualizing this property. Okay, so let's try to do the following. We're going to construct the so-called Pascal triangle, which will contain a separate cell for every n and k containing the value n choose k. So it is going to be constructed from top to bottom. So at the top we have just one cell containing the value 0 choose 0. The second row corresponds to n equal to 1, and it has two cells, 1 choose 0 and 1 choose 1. So in general, at every row it corresponds to some fixed value of n, and then it has all the values of n choose k, where k ranges from 0 to n. So when n is equal to 2, for example, k ranges from 0 to 2. So we have three cells. K is equal to 0, 1, or 2. When n is equal to 3, we have 4 such cells, and so on. Okay. Now let's see what our equality that we've just proved means in this triangle. So let me remind you, this equality n choose k is equal to n-1 choose k-1 plus n-1 choose k. So essentially it means that for every element in our triangle, its value is equal to the sum of its two top neighboring elements. So for example, what we know is that 5 choose 2, so the value of this cell is equal to the value of this cell plus the value of this cell. So in this particular case, n is equal to 5, n is equal to 5, and k is equal to 2. So by applying this formula, we have, so in this case, so this is 5 choose 2, and n-1 choose k-1 is 4 choose 1, which is exactly this cell, right? And then -1 choose k is 4 choose 2, okay, which is exactly this cell. And this holds actually for every cell, you know, for every, to be formal for every internal cell, right, in our table. Okay, now let me replace all these numbers with the actual values, and let's take a look. So first of all, we see that at the boundaries we have the value 1 everywhere. So why is that? Well, just because at the boundaries we have numbers like n choose 0 or n choose n. So n choose 0 is always equal to 1. So it is the number of ways of selecting an empty set. There is just one empty set. Okay, and n choose n is also equal to 1. Well, this is just because n choose n is the number of ways of choosing a subset of size n, and there is exactly one such subset, of course. So at the boundaries we have ones everywhere, right? And then every other element can be computed just by computing the sum. So for example, the 2 here can be computed as the sum of 1 plus 1. 3 here can be computed as 2 plus 1. 4 here can be computed as 3 plus 1. 5 here can be computed as 1 plus 4, and so on. So 3 is computed as 1 plus 2, 6 is computed as 3 plus 3, 10 is computed as 6 plus 4, and so on. And in fact, this gives us a way, like another way of computing the value of n choose k. So if, for example, you have large numbers n and k, one way of computing n choose k is to compute n factorial, then divided by k factorial, then divided by n minus k factorial. So it involves many multiplications and many divisions. At the same time, using Pascal's triangle, we can compute the value of n choose k just by computing some sums. That's as usual. So let's just declare the dictionary C such that C of nk is going to be equal to n choose k. Okay. Then we do the following: we loop through all the values from 0 to 7, and we do the following. First, we say that n choose 0 is always equal to 1, and n choose n is also equal to 1. In a sense, what we do here, we fill in our triangle, we fill it row by row, and at every row we first say that the values at the boundaries are equal to 1, and for every internal element in the row we compute it as a sum of 2 previous elements, right? And this is done here. So for all internal elements, we apply our formula. N choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. Okay? So when n and k are large, so it uses a lot of space for computing n choose k, but still, I mean, all the operations are just summations. And now, in the end, let's just do a sanity check. Let's compute this way. Let's print n choose 7 choose 4. I'm sorry. So what we expect is like 7 factorial divided by 3 factorial by 4 factorial, which is like 7 times 6 times 4 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. This is 3 factorial, and divided by 4 times 3 times 2 times 1. This is 4 factorial. We can cancel out this immediately, and then what remains is 7 times 6 times 5 divided by 3 times 2 times 1. So 6 is also cancelled, and what remains is 35. And the same result is printed by our recursive procedure. So once again, this Pascal's triangle gives us an alternative way of computing n choose k. Let's now use the Pascal's triangle to prove another useful property of n choose k. As you've probably noticed already, the Pascal's triangle is symmetric with respect to the center vertical line. So what does it mean? This actually means that if you start reading any row in this triangle, from left to right, then you get exactly the same as if you read it from right to left. For example, here we have 1, 4, 6, 4, 1, and if you read it from right to left, you get exactly the same sequence of numbers. So in terms of n and k, this means the following, that n choose k is equal to n choose n minus k. Okay? So let's prove this formula. First of all, you can prove this directly just by applying the known formula for n choose k. This gives you the following, well, slightly probably boring proof. So we know that n choose k is equal to n factorial divided by k factorial divided by n minus k factorial. Okay, this is just a formula, I'm sorry, for n choose k. On the other hand, let's apply the same formula for n choose n minus k. So at the top we have n factorial as usual. At the bottom we have, first of all, n minus k factorial. This is just repeated this element, and then n minus k, which is nothing else as just k factorial. Okay, then just by comparing these two numbers, it is easy to see that they are exactly the same, just with two terms swapped at the bottom, right, of our fraction. So this already proves this formula, but let's try to find some combinatorial meaning of this equality, which is actually more nicely illustrates the nature of this equality. So let's recall that n choose k, just by definition, is the number of ways of forming a team of k students out of n available students, right? On the other hand, n choose n minus k is essentially the same quantity, with the only difference is that in this case we are forming a team of size n minus k. But at the same time, note that when we form a team of k students, what we basically do is just we divide all our n students into two parts. So there are k students that go into a team, and there are n minus k remaining students. So that's why these two quantities are actually the same. So more formally, the proof goes as follows. If you would like to consider n choose k, then there are these possibilities. Okay, each possibility is some subset of size k, and there are n choose k of them. Right? Then let's also draw here on the right all possibilities of selecting subsets of size n minus k. So there are n choose n minus k of them. And there is a one-to-one correspondence between them. Namely, for each set of size k, we can find a unique subset of size n minus k. Namely, this is just a complement of this set. So if we have a set of n elements and we selected k of them, then the complement, so this is the size of size k, then the complement has size n minus k. So this establishes a one-to-one correspondence between sets of size k and sets of size n minus k, which basically proves that these two numbers are the same. We will now show that the symmetry is not the only remarkable property of Pascal's triangle. Namely, let's do the following. Let's compute the sum of all the elements in every row of Pascal's triangle. Okay? So what we see is that the sum in the first row is just 1. There is a single element. In the second row, it is equal to 1 plus 1, which is 2. In the third row, it is equal to 1 plus 2 plus 1, which is nothing else as 4. In the next one, it is 1 plus 3 plus 3 plus 1, which is 8, and so on. So you probably already see a pattern. So these are just powers of 2, and this is what we're going to prove now. So we're going to prove that the sum of all the elements in the nth row of the Pascal's triangle is equal to 2 to the n. Or put it otherwise, we're going to prove that n choose 0 plus n choose 1 plus and so on, n choose 1 minus 1, n choose n is equal to 2 to the n. Okay? So there are again two proofs. One is slightly boring, and it is completely formal. So we can show this just by induction on the number of row. So it definitely holds for the first row, and even for the several first rows as we've seen already, right? On the other hand, if we would like to prove the step of our induction, that is to prove that we need to prove that for the nth row the sum is equal to 2 to the n, assuming that for the previous row the sum is equal to 2 to the n minus 1. What we're going to show actually is that the sum in every row is twice the sum in the previous row. And we're going to show this just on a toy example to simplify things. So consider this row, 1, 4, 6, 4, and 1. So the sum is the following. Okay, now recall that this nice sum pattern in Pascal's triangle. So 4 is equal to 1 plus 3. 6 is equal to 3 plus 3. 4 is equal to 3 plus 1. Okay, let's now represent 4, 6, and 4 as 1 plus 3, 3 plus 3, and 3 plus 1. Okay, now let's regroup all our terms. Then what we get is 1 plus 1, 3 plus 3, 3 plus 3, and 1 plus 1. So in fact, and this holds in general, so in fact, if we regroup all the terms, if we express the sum in the current row via the sum in the previous row, then all the elements from the previous row appear exactly twice, which gives us actually that the sum in the current row is twice the sum in the previous row, which concludes the proof by induction. But now let's focus on the combinatorial proof of this equality. So recall that n choose k is, as usual, is the number of subsets of size k. When k ranges through all the values from 0 to n, we actually compute the number of subsets of all possible size from 0 to n, right? So the sum of all n choose k, where k ranges from 0 to n, is actually just the number of all possible subsets of our n element set. And this is known to be 2 to the n, and actually it follows from the product rule. Since you would like to compute the number of ways of selecting a subset out of our n element set, then for each of the n elements, there are exactly two possibilities. You either take it into your set or you don't take it. Okay, so the resulting number is 2 times 2 times 2 times 2, so n such terms, which is nothing else as 2 to the n. Okay, so another nice property is the following. It is now not about row sums, but about alternating row sums. So instead of just computing the sum in each row, let's compute the following alternating sum. So each subsequent term is taken with either with plus or minus sign. Okay? Then for every row except for the first one, what we see is that such a sum is equal to 0. So in the second row, it is 1 minus 1. In the next one, it is 1 minus 2 plus 1, which is 0 again. In the next one, it is 1 minus 3 plus 3 minus 1, which is again 0. So for some rows, it is immediate that it is equal to 0 just because they are symmetric. For example, this row is symmetric, so it has 1, 3, 3, 1, and one of these two elements appear with plus and one appears with minus. So it is not surprising that everything like telescopes or cancels out. For this row, it is also immediate. It is also symmetric, right? And each element is taken with plus sign and with minus sign. For other rows, it is not so immediate, but still it can be shown. And before this, let's state it formally. So for every row in our Pascal's triangle, except for the first one, the alternating sum is equal to 0. The alternating sum can be represented as follows. So instead of computing just the sum of all possible n choose k, we take n choose k with multiplier minus 1 to the k. So this is exactly, so minus 1 to the k provides this alternating of sums. So when k is equal to 0, minus 1 to the k is equal to 1. When k is equal to 1, minus 1 to the 1 is equal to 1. So minus 1 to the k is equal to -1 when k is odd and is equal to 1 when k is even. So that gives exactly alternation. Okay. So as we've discussed already, for some rows it is just immediate. For some other rows it also can be shown by using this sum pattern of Pascal's triangle. Namely, if you just represent this alternating sum of the current row via the previous row, I mean if you replace each element with the sum of two neighboring elements from the previous row, you will see that each element from the previous row is taken once with positive sign and once with negative sign, so everything cancels out. Okay, so this is just like a hand-wavy proof, a hand-wavy formal proof, but let's instead again focus on combinatorial proof. So we need to show that the alternating sum is equal to 0. If we take all the elements with the negation sign to the right, then what we need to show is that n choose 1 plus n choose 3 plus n choose and so on all for all odd k is equal to n choose 0, n choose 2 and so on. Okay, so what basically we need to show is that what basically stays on the left is the number of subsets of even size, and what stays on the right is the number of subsets of odd size. So this is also another nice property. What we are going to prove now, the combinatorial meaning of the equalities that we are proving is the following: that for every n greater than 0, an n element set has the same number of odd size subsets, as the number of even size subsets. Okay, so to prove this, once again, we are going to establish a one-to-one correspondence between all such subsets and all such subsets. Okay, and for this we are going to do the following. Let's fix any element x. Okay, and we can do this fixing just because n is greater than 0, so we have at least one element. Now we are going to establish this one-to-one correspondence as follows. So one-to-one correspondence is essentially like partitioning all the subsets into pairs, and we are going to form the pairs as follows. Let's say that the subsets A and B form a pair if they differ just by the element x. Namely, if one gets A by adding the element x to B. So what is written here is that A is B plus x. It is slightly informally, so more informally in terms of sets. A is equal to B union with a single element x. So this x embraces means that we are considering x as a set consisting of a single element x. And here we take a union of B and x. So for each once again, so B is a subset without x, and A differs from B just by adding x. So it is clear that this is indeed a one-to-one correspondence, right? So if we take all the subsets without x, and by adding x to them, we get exactly the same number of subsets, right? On the other hand, it is clear that exactly one in this pair of A and B has even size and exactly one of them has odd size, right? Because their size differ by 1. So which means that we actually splitted all our subsets into pairs, and in each pair there is one subset of odd size and there is one subset of even size. And this in turn means that there are the same number of odd size subsets as the number of even size subsets. Finally, here we show an example. If our ground set denoted by S has 4 elements, then on the left we list all its subsets of even size, and on the right we list all its subsets of odd size. So note in particular that we also count the empty set as usual. So the total number of subsets is 16, and as you see, the number of subsets of even size is 8, and the number of subsets of odd size is also 8. We conclude the current lesson with the well-known binomial theorem. So it states that the the coefficients of all the monomials in the expression a plus b to the power of n are actually the numbers from the nth row of Pascal's triangle. So let's check this for small values of n. Okay, so if one computes a plus b squared, then this is a well-known formula. It gives a squared plus 2ab plus b squared. So essentially the coefficients for the monomials here are 1, 2, and 1. And these are exactly the coefficients from this row. Another example, if we consider a plus b cubed, then it is 1 times a cubed plus 3 times a squared b plus 3 times ab squared plus 1 times b cubed. So these coefficients 1, 3, 3, and 1 are exactly the coefficients from the Pascal's triangle. Okay, let me also omit just the example for a plus b to the 4, but as you see, these are 1, 4, 6, 4, 1 are exactly the coefficients for the next power of a plus b. So more generally, a plus b to the n is equal to n choose 0 times a to the n plus n choose 1 times a to the n minus 1 times b plus and so on. So the general term in this expression is n choose k times a to the power of n minus k times b to the k, and so on. So the last term is n choose n, b times b to the n. So in terms of sum, it can be written as follows. A plus b is equal to sum overall k ranging from 0 to n of n choose k times a to the n minus k b times b to the k. Okay? For this reason, n choose k is also called a binomial or binomial coefficient. Okay, so it also has, so on one hand, n choose k is the number of ways of selecting a subset of size k out of a set of size n. On the other hand, it is also a coefficient of the monomial a to the n minus k times b to the k if you open the expression a plus b to the n, if you represent it just as a sum of monomials. Okay, so the proof of this theorem is actually straightforward. A plus b to the n is just the product of a plus b, and so on, a plus b n times. So if you start opening this expression, then of course from every term you need to select either a or b, right? And in particular, every monomial that you get has degree n. So you take, for example, kb's, and then you are forced to take also n minus ka's. And this gives you a monomial a to the n minus k plus times b to the k, right? So the degree of this monomial is n. Okay, so however, there are many ways of selecting kb's and n minus ka's, right? And the number of ways of selecting kb's is exactly n choose k, right? So you have n terms, and out of these n terms you are going to select k terms from which you are going to select b. So the number of these ways is n choose k, right? Exactly. Okay, so this also can be proved by induction using the Pascal's triangle. So by induction on n. So for n equal to 0 or 1 or 2 or 3 or even 4, we've already checked this, right? Now let me show you how the statement for n equal to 4 follows from the statement for n equal to 3. And this actually shows a general pattern. So in fact it uses the sum pattern of Pascal's triangle. Okay, so a plus b to the 4 is of course equal to a plus b cubed times a plus b. On the other hand, we already know the expression for a plus b cubed, and assume that we're proving this by induction, then all the coefficients just go from the third row of the Pascal's triangle. And now we need to multiply this expression with a plus b. So let's just do this. in a straightforward fashion. So a cubed plus 3a squared b plus 3ab squared plus b cubed, when we multiply it by a, we get the following expression. Okay? Then when we multiply it by b, we get the following expression. And they are aligned, now these two expressions are aligned so that we have these three terms here in the same columns. So as you see, when you compute the sum of them, this is essentially the same as computing, so this 4 comes as the sum of 3 and 1. This 6 comes as the sum of 3 and 3, and this 4 comes as the sum of 1 and 3. This is exactly the pattern in our Pascal's triangle. And this is true in general, not only for n equal to 4 and 3, of course. So this is a way of proving the binomial theorem by induction. Okay? Now let me show you also some slightly more complicated example, just to show you that binomial theorem allows us to compute the coefficients of all the monomials, not only for the case when we have just a plus b. Instead, we might want to compute the sum of, the fourth power of not just a plus b, but something like 2a minus b. In this case, what remains to be done is just to consider 2a and minus b as our new a and b. So we consider 2a minus b as the sum of 2a and minus b. And then for the sum of these two guys, we apply the binomial theorem. This gives us 2a to the fourth, then 4 times 2a to the cube times minus b times our second friend, then 6 times 2a squared times minus b squared, and so on. And then you just need to multiply these binomial coefficients with powers of 2 coming from 2a. Okay, and this finally gives you the following expression. So in particular, if you have something like 2a minus b to the 7th, for example, you don't need to actually multiply many terms. You just need to get the seventh row of Pascal triangle, and this will already give you all the coefficients. All what remains to be done is probably to multiply them with coefficients like 2, if instead of a plus b you have something like 2a plus b. Okay? Now let's also show several interesting consequences of the binomial theorem. For example, if we set a and b equal to 1, then what we get on the left, so instead of a plus b to the n, what we get is 1 plus 1 to the n, that is just 2 to the n. Okay? And this is what we get here. On the other hand, a to the k and b to the n minus k is always equal to 1, because a and b is equal to 1. So on the right, what we have is the sum of all binomial coefficients. So this gives us another proof of the fact that the sum of all binomial coefficients is equal to 2 to the n. Okay? On the other hand, if we set a equal to 1 and b equal to minus 1, then on the left we have 0, right? Because we have 1 plus minus 1 to the n. On the other hand, on the right, what we have is just an alternating sum. Okay, so this gives us another proof of the fact that the alternating sum is equal to 0. And let me recall you also the combinatorial meaning of that. This means that for any subset, for any n greater than 0, the number of odd size subsets is the same as the number of even size subsets. And the combinatorial meaning of the previous equation is that the number of subsets of an n-element set is equal to 2 to the n. Okay, finally let me show you one more consequence, the one that we haven't seen before. So if we set a equal to 1 and b equal to 2, then what we get on the left we have a plus b, which is 3, so 3 to the n, and on the right we have binomial coefficients, and each binomial coefficient n choose k is multiplied by 2 to the k. Okay, so we have this nice formula. 3 to the n is equal to n choose 0 plus n choose 1 times 2 plus n choose 2 times 2 squared plus and so on, n choose n times 2 to the n. So this is an interestingly looking example, but it also have a combinatorial meaning. So let me give you a combinatorial proof of this equation. So what we have on the left here may be viewed as a number of ways of composing a word of length n out of 3 symbols, denote them by x, y, and z. So 3 to the n is of course the number of such words, because for every of n positions you have 3 possibilities, x, y, and z. So now our goal is to express this number of words as this sum. And this is what we're going to do now. So let's compute it as follows. So n choose 0 is the number of all words of length n that consist of only of letter x. Okay, so n choose 0 is actually 1, so when there is exactly one such word, so it is just x, 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 n times, right? Okay, so we justified this. Now what we're going to compute next is the number of words containing exactly n minus 1 letters x. Okay, so how to compute it and why it is equal to n choose 1 times 2? Well, it is equal to this expression because of the following fact. To compose such a word, we first need to select exactly one position where x does not appear. So we can do this in this many ways, n choose 1. And then for this position, we need to choose either y or z. So we multiply it by 2. Okay, so this is once again the number of words of length n that contain exactly n minus 1 letters x. Okay, let me finally show you the next one and the pattern will emerge. So this is, as you might guess already, exactly the number of words of length n that can contain exactly n minus 2 letters x. Why is that? Well, again, because to form such a word, we first need to select 2 places where there is no x. And for each of these 2 places, we need to select either y or z. So first of all, there are n choose 2 choices of these 2 places, and then for each of these 2 choices, we need to select either y or z. So it is 2 times 2. Okay, and this gives us n choose 2 times 2 squared, and in general, if we would like to compute the sum of the number of words that contain exactly n minus k letters x, then we first select k positions where x does not appear, and then for each of these k positions we select either y or z. This gives us n choose k times 2 to the k. Now let's apply what we've just learned to solve several problems. So the first problem is actually easy. So the question is, what is the number of ways of selecting 5 cards out of 52 cards, out of a standard deck consisting of 52 cards? So one such combination is shown here on the slide, and the question is, of course, it is just 52 choose 5, which is roughly 2.5 million. Okay, now let's slightly change the problem. Now we are looking for a number of ways of selecting 5 cards such that 2 of them are hearts and 3 of them are spades. Okay, now we see that we can arrange our 5 cards as follows, such that first we have 2 hearts and then we have 3 spades. Okay, then to count such number of ways, we actually need to realize that for the first 2 cards, for each of the first 2 cards, there are 13 possibilities, all 13 hertz cards, right? So, and among these 13 cards, we need to select 2. And the same for spades. We need to select 3 spades from 13 possibilities. So by the product rule, the answer is just 13 choose 2 and times 13 choose 3, which is roughly 22,000. Okay? So the next problem is about numbers. In this case, we are interested in non-negative integers with at most 4 digits, such that at least one of their digit is equal to 7. So in this case, it turns out that it is easier to compute the complement of what we need to compute. Namely, let's compute the number of integers, of non-negative integers with at most 4 digits that do not contain 7 as a digit. Okay, it is not difficult to compute. So there are 4 digits, and for each of 4 possibilities, we have just 9 choices. I mean, all the 10 digits except for 7, which means that there are 9 to the 4 such possibilities, and the total number of 4-digit numbers, at most 4-digit numbers, is 10 to the 4. Which means that we need to subtract 9 to the 4 from 10 to the 4, which gives us something like 3000 and roughly half. And we can double check this using a simple for loop in Python like this. So let's just consider all possible tuples of 4 digits, and for each such tuple we check whether 7 is present in this tuple or not. If yes, we just increase our results in count by 1. So in the end we print count, and to double check we print also the value of 10 to the 4 minus 9 to the 4. So as we see, this is exactly the same number. Okay, so the next one is the following also typical problem. We would like to compute the number of non-negative integers with at most 4 digits, such that the digits are strictly increasing. Okay, so this is probably a slightly more complicated example. So in this case, we need to realize that first all the digits all the 4 digits in our number are actually different. Okay, but this in turn means that our goal is just to select 4 different digits out of 10 possible digits, and then what we need to do is to arrange them in increasing order, right? But this in turn means that the answer is nothing else as 10 choose 4, I'm sorry, which is equal to 210. Once again, let's double check this. Let's implement the following simple procedure. So it just ranges through all possible tuples of 4 digits. So through all possible 4, and all the possibilities are digits from 9 to 10. Then if the 0th digit is smaller than the first one is smaller than the second one, and the second one is smaller than the third one, meaning that the digits are indeed increasing, then we increase the count, and also we print the resulting number. In the end, we print the count. Okay, so then if we run this program, then it will start printing numbers like 0, 1, 2, 3. I mean, these are just digits, these are not numbers. Then 0, 1, 2, 4, and so on. So something is missing here in the middle of this list, and then the end of this list looks as follows: 6, 7, 8, 9, which is kind of the largest 4-digit number with increasing digit. And in the end, we also print the count, which is indeed 210, which is nothing else, once again, as 10 choose 4. Okay, finally, let's revisit the following problem. So we are given a board, for example, an 8 by 8 chess board, and we have a piece whose initial position is at the cell 0, 0. And what we would like to do is to count the number of ways to get, for example, to the cell 5, 3, to the cell whose row is 5th one and whose column is the 3rd one. So we would like to count this number of ways, assuming that in a single move this piece moves either to the right or moves up. Okay, so first of all, it is clear that the number of moves should be exactly 8. I mean, in any possible movement from this position to that position, the piece should make exactly 8 moves. Why is that? Well, just because each time we either increase the row number or we increase the column number. Initially, the row number and the column number is equal to 0, and in the end, the row number is equal to 5, and the column number is equal to 3. So at with each move, the sum is increased by exactly 1. Initially it is 0, in the end it is 8. So the number of moves must be equal to 8. And this gives us a hint. So we need to make 8 moves. On the other hand, we know for sure that the number of moves to the right should be exactly 3. If we make less than 3 moves to the right, then we will not be able to reach the third column. If we make more than 3 moves to the right, then we will not be able to return back to the third column. This is on one hand. Okay? On the other hand, if you consider any such combination of 8 moves, such that among these 8 moves there are exactly 3 moves to the right, then we reach the position 5, 3. Well, why is that? Just because if there are exactly 3 moves to the right, this means that after this we are at the third column for sure. And since there are exactly 3 moves to the right, all the other moves are going up. Okay, and this in fact means that we end up in the fifth row, so exactly in our final position. And this all allows us to conclude that the number of such possibilities is 8 choose 3, which is nothing else as 56. Well, it is also interesting to note that we could also compute this number as the number of ways of selecting moves up, 5 moves up among 8 possible moves. This would give us another solution, which is 8 choose 5. Okay, so this is the same as selecting 5 moves up among all 8 moves. At the same time, 8 choose 5 is equal to 8 choose 3, as we know already, right? This is a property of these binomial coefficients. Finally, let me also show you that the same result can be achieved by drawing an analogy to the Pascal's triangle. Okay? So now let's do the following. For every cell in our board, we are going to compute the number of ways of getting to this cell. First of all, for some numbers it is easy. Okay? So we know that for all these cells it is equal to 1, and for all these cells it is also equal to 1. For example, for this cell, the only possible way to get there is to go to the right. Okay? Now let's do the following. Let's start computing this number for all other cells. So for example, we show 2 here. Why is 2? Well, this is just because for every cell in our board, there are 2 possibilities of the previous move before getting to this cell. So we might go there from this cell or from this cell. Okay? So, and in fact, it is not difficult to see that we go either this way or we go either this way. So in this case, it is easy to see. It is equal to 2. But also this is true in general. If we have some particular cell here, for example, then any correct way of getting to this cell, either its last move is either from this neighbor from the left or from the neighbor from below. Okay, which basically means that if we have a number of ways here which is equal to A and the number of ways here which is equal to B, then the number of ways which we need to compute here is A plus B. So the numbers that we compute satisfy this nice property that in every cell the value is equal to the value of its neighbor to the left and the value of its neighbor below. Okay? And this allows us to fill in this table as follows. So here we have 3, just because it is the sum of 2 and 1. Okay? Now let's continue filling in this table. So this 3 is equal to 1 plus 2. Okay? Finally, this 4 is equal to the sum of 1 plus 3. Well, not finally, I'm sorry, we're still going to fill in this table. So this 6 is equal to 3 plus 3, and so on. This 4 is equal to 1 plus 3. Now let me continue doing this by hand. So here we put 5 because it is 4 plus 1. Here we put 10 because it is 4 plus 6. Here we put 10 because it is 4 plus 6. And here we put 5. Then here we put 15, here we put 20, 15, and also 6. Here we put 35, here we put 21, and finally here we get 56. Exactly, so for this cell that we were interested in, we get exactly the same result. And you've probably already noticed that what we were doing is actually filling in the Pascal triangle, whose like top vertex was actually rotated to be here. So this is like the first, the zeroth row of Pascal's triangle. This is the first row of Pascal triangle. So this is 0, this is first, this is second one, this is third one, this is fourth one, this is fifth one, and so on. So this actually, this cell 5,3 actually lies on the eighth row of Pascal triangle, and we basically know that at eighth row what all the values of the form 8 choose something. So this particular cell is 8 choose 5. So this is another proof of the fact that to get to the cell 5,3 we need the number of ways to do this is 8 choose 5.
Hi, I'm Vladimir Podolsky, and today we are going to talk about combinations with repetitions. Let's review our knowledge. We have considered selections of k items out of n possible options. And there are several variations to this model. We can consider ordered selections and unordered selections, and we can consider selections with repetitions and without repetitions. That is, we can allow to include the same option several times in the selection, and we can not allow to do that. So let's consider a simple example. Suppose k is 2 and there are 3 options A, B, and C. So the simplest case is the case of ordered selections with repetitions. Here we have 9 possible selections. We can pick the first item in 3 possible ways, and we can pick the second item in also 3 possible ways. Next, we have considered ordered selections without repetitions. So now we can pick the first item again in 3 ways, but we can pick the second item only in 2 ways because we cannot repeat the same item twice. Okay. Next, we considered unordered selections without repetitions. And here we have 3 options, AB, AC, and BC. This is similar to the case above, but now we don't have order. So above we counted all of these pairs twice because of the order. Okay, and now we have the fourth possible type of selections. We have unordered selections with repetitions. This is similar to the right case, but now we also allow selections where the same item is repeated twice. Okay, let's review what we have learned so far. We considered ordered selections with repetitions. These are just tuples. We can pick any item in n possible ways. There are k items, so we have n to the k possible selections. We also considered ordered selections without repetitions. These were k permutations. Now for the first item we have n options, for the second we have n minus 1 option, and so on. So the answer is n factorial divided by n minus k factorial. Next, we considered unordered selections without repetitions. These are combinations, and the answer was n choose k. And now we have the fourth square here, unordered selections with repetitions, and we haven't considered it yet. So this remains unclear. But before we start thinking about it, let's see. Maybe it's not relevant. Maybe this type of selections doesn't occur anywhere. Let's consider the following example. There are k voters that vote for one of n candidates. So here is a ballot. This is a secret ballot, and each voter votes for one of the candidates, maybe candidate 1, maybe candidate 2, and so on, maybe the last candidate. So all votes equally matter. That is, it doesn't matter in which order votes are submitted. We can think of this as an unordered selection. Also, candidates can be voted for several times by several different voters. So voters as a group pick k people out of n possibilities with repetitions. So this is our setting. let's consider the following problem. We have an unlimited supply of tomatoes, bell peppers, and lettuce. We want to make a salad out of 4 units among these 3 ingredients. We do not have to use all 3 ingredients, we just have to pick 4 units among 3 options. How many different salads we can make? Let's see what we have in this problem. We pick 4 items out of 3 options with repetitions. And the order doesn't matter. If we pick items in the different order, then this is still the same salad. So this is our setting, combinations with repetitions. Order doesn't matter, we allow repetitions of options. We still do not know how to compute the answer immediately, we do not have a formula. What we will do in this example, we will list all possible salads and then we will count them. But we would like to do it wisely. We would like to build up some intuition for the future solution of this problem in general. So let's look at the picture. We will denote tomatoes by red circles, bell peppers by yellow circles, and lettuce by green circles. So we have 4 ingredients, and for example we can pick a salad like this, or we can pick the salad like this, and note that these are just the same salads, order doesn't matter. We have 2 units of tomatoes, 1 unit of bell pepper, and 1 unit of lettuce. So since the order doesn't matter, let's do the following. Let's draw on our picture tomatoes first, then bell peppers, then lettuce, and let's do this always. So this way we will not count the same thing twice. So this is the same salad, but now we have ordered it. Okay, now we have to list all possible salads. So we have to do it in some ordered way, in some reasonable way. Let's consider, let's do the following. Let's consider all possible numbers of tomatoes in the salad. Let's consider all possible cases, and we will count the number of salads in each case separately. Okay, let's proceed to this. Here is our salad, and let's start with the simplest case, the case of 4 tomatoes. Here it is, and there is only 1 salad with 4 tomatoes, because there is no room left for other ingredients, so 1 salad. Let's proceed to the next case, the case of 3 tomatoes. Now we have to pick the last ingredient. It cannot be a tomato, because we have only 3 tomatoes now, and so it can be either bell pepper or lettuce. So bell pepper, lettuce. So there are 2 salads with 3 tomatoes. Okay, next case, 2 tomatoes. Now we have 2 ingredients left, and they can be either 2 bell peppers, 1 bell pepper and 1 lettuce, and 2 lettuce. Okay, so we have 3 salads in this case. Now, the case of 1 tomato. Now we have 3 ingredients left. It can either be, all of them can be bell pepper, 2 bell peppers and 1 lettuce, 1 bell pepper and 2 lettuce, and 3 lettuce. So there are 4 salads now. And the last case, the case of 0 tomatoes. There are no tomatoes in our salad. Then either all ingredients can be bell pepper. There can be 3 bell peppers and 1 lettuce. There can be 2 lettuce and 2 bell peppers, 1 bell pepper and 3 lettuce, and all of them can be bell peppers. So these were 5 cases. So in case of 0 tomatoes, there are 5 possible salads. So we have considered all possible cases of the number of tomatoes. And in total, if we sum this up, we will see that these are 15 salads. In total, we have 15 salads. So here is the list of all of our salads. In the first column, we can see 1 salad for 4 tomatoes, 2 possible salads for 3 tomatoes, then 3 possible salads for 2 tomatoes, then 4 options for 1 tomato, and finally 5 possible salads for 0 tomatoes. So here we are all in the picture, there are 15 options in total, and we are done. Okay, the solution looks very structured. For 4 tomatoes we have 1 salad, for 3 tomatoes we have 2 salads, and so on. Each time the number of salads increases by 1. If we increase the size of the salad, but keep the number of ingredients the same, then the same structure holds. So the solution will have the same structure. But if we increase the number of ingredients, then the picture becomes more complicated. Yet the same strategy works. We can still count the number of salads in the same recursive manner. Let's consider the following problem. We have now unlimited supply of tomatoes, bell peppers, lettuce, and eggplants. So we want to make a salad out of 7 units among these 4 ingredients. Again, we do not have to use all ingredients, we just have to pick 7 units among them. How many different salads we can make? Okay, we can use recursive counting here as well as in the previous problem. But now we would like to obtain a formula. And this will be a general solution. Our solution will work for any number of ingredients and any size of salad. Okay, so here is a picture again. Now tomato is red, bell pepper is yellow, lettuce is green, and eggplant is purple. Okay, now we have 7 ingredients. Here is an example of salad, but note again that the order doesn't matter. So for our convenience, let's just list the tomatoes first, then bell peppers, then lettuce, then eggplants. So here is our salad. The solution to the problem is non-trivial, so we will break it down to several simple ideas. Okay, the first idea. What information do we need to specify the list of ingredients? What is enough? Okay, it turns out that it is enough to say where in this list we switch from tomatoes to bell peppers, where in this list we switch from bell peppers to lettuce, and where we switch from lettuce to eggplant. So we can mark these places, and then this is enough information. We can forget about colors. Now we do not need colors. We can reconstruct them from what is on the picture. Okay, next, second idea. We do not even need these text descriptions for tomatoes, bell peppers, and eggplants. We can remove them, because we know that this first place corresponds to the switch from tomatoes to bell peppers. We have ordered ingredients in this way. The second corresponds to switch from bell peppers to lettuce, and the last one from lettuce to eggplant. Okay. And finally, the third idea. We can represent these places of switches by some special signs, some delimiter signs. Let's do it. Okay. We have done this. So now we have the first delimiter between tomatoes and bell peppers is after the second ingredient. Then the next delimiter is between bell peppers and lettuce, and the last delimiter is between lettuce and eggplant. Okay, and note again that the salad can be still restored from the current picture. We can just color the ingredients as we described before, and we will restore the original salad from this picture. Let's do a small sanity check right now. What happens if in our salad there are no, say, bell peppers? So will the picture make sense? So how will it look like? Can we represent such a salad with such a picture? It turns out that this is fine. We will have a picture like this. The first and the second delimiter will be right next to each other. There are no ingredients in between of them. So in case of this particular picture, we have salad with 2 tomatoes, 3 lettuce, and 2 eggplants. So this is fine. Our picture still represents such salads. Okay, now let's proceed with the proof. What do we need to specify to fix a particular salad? Okay, now it turns out that this is simple. We need just to specify where to place 3 delimiters among these 2 positions. If we specify 3 delimiters there, then our salad is ready. Okay, and these are exactly combinations. So we have 10 possible options, and we have to pick 3 out of them without order. So the answer here is just n choose 3, which is 120. Note that this is 120, not 120 factorial. So the answer to the problem is 120. Okay, let's review how we got there. Here is the original problem, and let's review our main ideas. First, order salad in a convenient way. Order doesn't matter, so we can order the ingredients in the way we like. So that turned out to be very useful. Next, salad can be determined by delimiters between types of ingredients. So we introduce delimiters, and once we introduce them, we do not have to provide any more information. We have delimiters, we know where ingredients change. And final idea is to place delimiters in the line with other ingredients. And then we have a list of 10 options, 7 units plus 3 delimiters, and we have to pick 3 delimiters among them. And that's what we already know how to do. So if we consider number of combinations of size k out of n objects with repetitions, then the number of such combinations is equal to k plus n minus 1, choose n minus 1. So here is the connection to the previous problem. Size of the combinations is size of the salad. Number of objects is the number of ingredients. And the same argument works. So just our previous argument was general. So we can substitute 7 and 4 by k and n, and the same proof works. Let's just recollect briefly why we have k plus n minus 1 here and n minus 1. Why not, for example, k plus n and m? Just so it looks natural, but instead we have k plus n minus 1 and n minus 1. So recall that n ingredients in the salad mean that we need to place n minus 1 delimiters between them. So here is where n minus 1 comes from. So in the end of the solution, we will have to choose n minus 1 positions in the line of k plus n minus 1 elements. K stands for the size of the salad, for the number of units of ingredients in the salad, and n minus 1 is the number of delimiters. Okay. Now let's get back to our table we had in the beginning of this lesson. We can consider different variations of selections of k items out of n possible options. And so there are several variations. There are ordered and unordered selections. There are selections with repetitions and without repetitions. Let's briefly review them. So ordered selections with repetitions are just tuples. There are n to the k of them. Next, ordered selections without repetitions are k permutations. There are n factorial divided by n minus k factorial of them. Then we proceed to unordered selections. Unordered selection without repetitions. They are combinations, and there are n choose k of them. And in this lesson, we consider the final cell of this table, unordered selections with repetitions, and it turns out that binomial coefficients helps here as well. So the number of combinations with repetitions is equal to k plus n minus 1, choose n minus 1. Hi, I'm Vladimir Podolsky, and today we are going to discuss various problems on combinatorics. Let's consider the following problem. There are 4 people and 9 different assignments. We would like to assign each person one assignment. How many ways do we have to do it? Okay, in this problem we have to count selections of assignment for 4 different people. Peoples are different, so the selections are ordered. And no assignment can be given to 2 persons, so we do not allow repetitions. So we are just dealing with k permutations. Okay, let's consider the table. There are 4 persons, there are a number of options for them. For the first person, we can pick an assignment in 9 possible ways. For the second person, there are only 8 possible options. For the third, there are 7 possible options. And for the last person, there are 6 possible options. So these are just k permutations. Okay, and the answer is 9 times 8 times 7 times 6, 3024. Okay, and the problem was rather simple. We needed just to count permutations. The main difficulty was to understand that we need to count permutations. Now let's proceed to the next problem. Again, we have 4 people. Again, we have 9 different assignments. But now we would like to distribute assignments between people. So each assignment should be assigned to one of the persons. And every person can receive arbitrary number of assignments from 0 to 9. How many ways do we have to do it? Okay, now the difference is that the person receives several assignments in this problem. Let's try to solve this problem, and we can try to look at persons one by one. Okay, the first person is assigned an arbitrary subset of assignments. So we know how to count the number of subsets. We have done this before. But if we look at the second person now, the number of options left for him depends on what we have chosen for the first person, how many assignments we have given to the first person. So now counting the number of options for the second person looks problematic. Okay, the problem seems tricky, and we need some idea. And we have this idea. The idea is the following. Let's look at this problem from the other point of view. Let's not give assignments to people. Let's assign people to assignments. Let's look from the position of assignments. And then everything looks simple. So we have 9 possible assignments, and let's see what options do we have for each assignment. For the first assignment, we have 4 options we can assign to any person. For the second, the same, and for the third one, and so on. So each assignment can be given arbitrarily to one of 4 persons. So in total, we have 4 times 4 times 4, and so on, 9 times 4 to the 9, 262,144 possible ways to do it. And note that in this problem we just needed to count tuples. It turned out to be very simple, but it looked hard in the beginning, so we also needed to switch to the other point of view. Let's consider the following problem. We have 15 identical candies, and we would like to distribute them among 7 kids. How many ways do we have to do it? Let's look at the problem in the following way. Each time we give a candy, we choose one of 7 kids. Okay, repetitions here are allowed. The same kid can receive more than 1 candy, and in fact this is unavoidable. There are 15 candies and just only 7 kids. Candies are identical, so the order doesn't matter. If some kid receives the first candy or the second one or the third one, it doesn't matter. They are all the same, so we don't care about the order here. So we are dealing with combinations with repetitions. Order doesn't matter, repetitions are allowed. And here the number of candies is the size of a combination. So each time we give a candy, we pick one of the kids. So the size of our selection is 15. And the number of kids is the number of our options. Each time we give a candy, we pick one of 7 options, one of 7 kids. So the answer here is obtained by a formula we already have. It's 15 plus 7 minus 1, choose 7 minus 1. And which is 21, choose 6, which is 54,264. Okay, now let's consider a similar problem. Again, we have 15 identical candies. Again, we would like to distribute them among 7 kids, but now we would like to do it in a more fair way. We would like that each kid receives at least 1 candy. Okay, the previous solution doesn't work because now we have an additional restriction. There are less combinations here, and we have to do something else. The previous solution doesn't work directly. Okay, but so what we can do? It turns out that we can reduce the problem to the previous one. How we can do it? The idea is the following. We know we have a restriction that each kid has to receive at least 1 candy. So let's just do it. Let's just give each kid a candy and then proceed to give other candies. But let's just give each kid 1 candy and see what is left. Now we are left with 15 minus 7, which is 8 candies. And now we have to distribute them in the same way as in the previous problem. We have already satisfied our restriction. We have already given each kid 1 candy. We are left with 8 candies. And we have to just apply the same argument as in the previous problem. So again, we have combinations with repetitions, but now the size of the combination is 8. This is the number of candies that is left after we gave each kid a candy. And the number of options, the number of kids is 7. So the answer here is 8 plus 7 minus 1, choose 7 minus 1, which is 14, choose 6, which is 3003. It is interesting to compare the answer to this problem with the previous one. So here the answer is 3003. And in the previous problem, the answer was 54,264. So there are a lot of ways to distribute candies between 7 kids. and only in tiny fraction of them each kid will receive at least one candy. Now let's consider the following problem. How many non-negative integers below 10,000 do we have such that the sum of their digits is equal to 9? Okay, we can consider numbers below 10,000 as sequences of 4 digits, and we can try to look at this problem from the position of numbers. We can try to see how many options do we have for the first digit, for the second digit, and so on. So for the first digit we have 9 options. But already for the second one this is unclear. If the first digit is for example 9, then there is just one option for the second digit. If the first digit is 0, then there are 10 options for the second digit. So this is unclear, this approach doesn't seem to work. And instead we can try to do the following. Here is the idea. Let's look from the other side again. Okay, we have 4 positions, and we would like to distribute weight 9 among them. So we assume that initially, in the beginning, all positions are 0, and then we add 1 9 times. And this way we will obtain all possible 4-digit combinations with sum of digits equal to 9. Okay, order doesn't matter. So if we add 1 to some position on the first step, and on the second step it doesn't matter. So we still add 1 to the same position. Also, repetitions are allowed. So here we are dealing with combinations, with repetitions of size 9 among 4 options. Okay, and we know how to count them. The answer is 9 plus 4 minus 1. We have 4 options, so we have 4 minus 1 here. 9 plus 4 minus 1, choose 4 minus 1, which is 12, choose 3, which is 220. Now let's proceed to a very similar problem. How many non-negative integer numbers do we have below 10,000 such that the sum of their digits is equal to 10? In the previous problem we had 9, now the sum is equal to 10. The problem looks very similar to the previous one, so probably we should just try the same approach. Now we have to distribute 10 ones between 4 positions. Again, we have combinations with repetitions of size 10 among 4 possible options. And the answer is 10 plus 4 minus 1, choose 4 minus 1, which is 13, choose 3, which is 286. Okay, is everything right? So have we done everything correctly? So let's just check. Let's count all of these combinations directly. So for this we can just run the following code. This code goes through all 4-digit combinations and increase the counter if the sum of all digits is equal to 10. And if we run this code, we obtain the following result, 282, which is not equal to our answer. Our answer was off by 4, not by 4 factorial, by 4 exclamation mark. So what went wrong? What we have done wrong? What happened? Maybe we can see it from this code we have, from comparing this code to our solution. And it is not hard to see. If we know that there is a problem, it is not hard to see where it is. When we applied our approach, we also counted the following. We counted cases in which we assigned all 10 ones to the same position. And this is not allowed in digits. Digits ranges from 0 to 9. So we shouldn't have counted this. So what should we do now? And okay, the idea is simple. We can just fix our old solution. Let's just subtract the number of things we shouldn't have counted. Okay, and let's count them. Let's count the wrong combinations we had before, and let's subtract them. Okay, what exactly we shouldn't have counted? We shouldn't have counted assignments of all 10 ones to the same digit. And there are just 4 of them. We can assign all 10 ones to the first position, to the second one, to the third one, and to the fourth one. So there are just 4 of them, and the correct answer to this problem is 286 minus 4, which is 282, which now coincides with our experiment. let's consider the following problem. We would like to count how many 4-digit numbers do we have, such that their digits are not increasing from left to right. And in this problem, we assume that 3-digit numbers, 2-digit numbers, 1-digit numbers are also 4-digit numbers. We just start with 0. Okay, we can try to look from the side of positions in the numbers. We can try to count options for each position and then apply product rule to solve this problem. But it turns out to be complicated. This approach doesn't work. We have 10 options for the first position, but if we already consider the second position, since the number there should be at most the number in the first position, the number of options depends on what we have chosen for the first position. So this approach doesn't work, and we have to do something else. And the idea is again to look from the other side. Okay, again we have 4 digits, and we pick digits from 0 to 9 for each position. And okay, note that once we picked 4 digits to place to these positions, our number is uniquely determined. Indeed, suppose we have picked 4 digits, 3, 4, 3, 7. Then we can position them in these 4 digits in a unique way. We can place 7 only on the first place, 4 only on the second place, and then 3 and 3. The reason is that the digits in the number should not increase. So there is a unique way to place 4 digits in our positions. So, and note that order of the picks doesn't matter, so anyway we will have to reorder numbers, and repetitions are allowed. So again, we are dealing here with combinations with repetitions of size 4 from 10 options. So we need to pick 4 numbers from 0 to 9, and the order doesn't matter, and we allow repetitions. Okay, and the answer is known to us. The answer is 4 plus 10 minus 1. Choose 10 minus 1, which is 13, choose 9, which is 715. Consider the following problem. We have 12 students in the class, and we would like to split them into working groups of size 2 to work on the same assignment. How many ways do we have to do it? Okay. This problem is more tricky than previous problems. There are several ways to solve it, but anyway, we need to combine several ideas we had before. Okay. One of the solutions goes by looking from the position of working groups. We have to pick, let's just pick the first working group. We have to pick 2 people out of 12 into the first working group. And order in the group doesn't matter, so we are dealing with combinations. So there are 12 choose 2 ways to do it. Okay, now let's proceed to the second group. We have 10 people left. And again, the order doesn't matter, again, combinations, and there are 10 choose 2 options there. And so on. If we go through all of the groups, and each time we have to, so in total we have to multiply options for each group, then we have 12 choose 2 times 10 choose 2 times 8 choose 2 times 6 choose 2 times 4 choose 2 times 2 choose 2 options. Okay, so we obtain this. Is this all? Are we done? It turns out that no, we are not, and let's see what is the problem. Let's, for our convenience, enumerate people by numbers from 1 to 12. And let's consider, for example, the following splitting into groups. Here is the first group of size 2, then 1 and 5 the second group, and so on. And we have counted this splitting into groups, but also we have counted this splitting into groups separately. And note that the difference is only in the first 2 groups. They are just switched between each other. But note that the order between groups doesn't matter, it's still the same splitting into groups. So we have counted the same splitting into groups twice. Okay, our solution is wrong, so what do we have to do now? Should we start from the beginning? Okay, it turns out that we do not have to. We can just fix this solution by applying the old idea we already had. Note that we have counted each splitting 6 factorials times. Why 6 factorial? We counted each splitting as many times as there are permutations of 6 groups. And we know that there are 6 factorial permutations. So we have counted each splitting into groups 6 factorial times. So now a first attempt, the answer was this one. And now we know that we have counted each splitting 6 factorial times. So to get the right answer, we have to divide our first attempt by 6 factorial. And so the answer is this one. So it's the same product of binomial coefficients divided by 6 factorial. And we can write down this expression. In the numerator, we will have 12 times 11 times 10 and so on times 1. In the denominator, we will have 2 times 2 times 2 and so on 6 times and 6 factorial. And if we look at this expression, then when we calculate it, then we will have that it is equal to 10,395. So let us summarize what we have learned from the beginning of this course. We have discussed several standard settings in combinatorics. And it turns out that vast majority of counting problems that we meet in practice fall into one of these settings, so we can solve them using one of these settings. There are, of course, more complicated situations that we haven't discussed. And there are so complicated situations that are still unresolved, and combinatorics is an active field of studies. And next week we will proceed to probability, where in particular we will need the knowledge we obtained in combinatorics.
We start this part of our course devoted to probability theory, and I would like to start with some general remarks. Actually, probability theory is rather strange. It tries, so to say, to predict the unpredictable. So, for example, a standard object of probability theory is coin tossing. So imagine you go to a restaurant, you want to decide who will pay, and so if you can take a coin and toss the coin, and then the idea is that nobody can predict this. So somehow you don't know in advance who will pay, and both have somehow equal chances to pay. So you see that this is tail, and then you decide who pays. And the idea of probability theory is somehow that you can predict something about the coin tossing. Let me explain. So imagine we do not the one coin tossing, but many of them. So we toss it many times and we record the results. For example, if 1 is tail and 0 is head, here is this tail, head, and so on. So we can count how many heads and tails we have in this sequence, and it turns out that usually zeros and ones appear equally often, not exactly equal number of zeros and ones, but actually they are quite close. So let's look at this in this example. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Hopefully I'm correct, but 16. And the total number is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4, 5, 6, 7, 8. So it's 16 of 28. It's not exactly half, because half will be 14 of 28, but quite close. And we can try to make these computations for different number of coin tosses and compute the frequency of ones. The frequency of 1 is the number of ones divided by the total length. And the prediction of probability theory is that it should be close to 1/2. And here let's do it actually, and one can draw a graph. So you see this is 1, 1, 0, 0, and here is the number of experiments, and here is the frequency. So you see that we start with ones because there are 2 ones in it. And here then there is a long series of zeros and frequency goes down. So now we are here. Then there is two ones, we are here, 2 zeros, and so on. So there are some oscillations, but at the end the oscillations are small, and after 100 coin tossing we are close to 1/2, a bit more. So let's see what happens later for 1000. And you see this initial part is somewhere here. So there were oscillations, but then oscillations become smaller, and at the end, rather close to 1/2. And if we make 10,000 random experiments, you see that it's even better. So now the oscillations are very, very small part of the picture. At the end, we have almost 1/2. It's even hard to see whether it's more than 1/2 or less. So for 10,000, the frequency is very close to 1/2. Probably you won't believe me that I make 10,000 coin tossing, and indeed this is not real coin tossing. This is some experiment, physical experiment, which should behave in the same way. It was produced specially for long sequence of bits which behave like coin tossing. It's random bits, so to say. Another physical device to show the laws of probability theory, it was designed specially for this. This is what is called Galton board, and also the other name is bean machine. So if you look at Wikipedia page, it's called bean machine. What it is, it's a vertical thing. You see the picture, I think, of a real machine from Wikipedia. And what is happening? So the beans go here, and then they fall down through this hole, and there is some kind of cylinder, and beans go down, and what is random here, they can go left or right. And the idea is that you cannot predict for individual bean whether it will go left or right, but half of them normally will go, approximately half will go to the left, and then go to the another half go to the right. And after that they go fall down, and they see another, meet another cylinder, and in this cylinder again they can go left or right. So at the end they are collected in these boxes, and what is interesting here, that the central boxes are full, and the boxes far from the center are almost empty. So there is some kind of concentration effect. These beans have a tendency to concentrate near the center of the machine. This is the effect which should be explained. You can also look at the video. A Wikipedia page has a nice video how it works. Now the analysis of this machine. So we assume, this is assumption about real world, we assume that at each level beans are split evenly. So here if we take it, the total number of beans we denote as 1, then half of them goes here and half of them goes here, and then they go here. No, okay, here is also 1/2 and 1/2, and here we get 1/4 and 1/4. Just this 1/2 is split into two equal parts. And here we also have 1/4 and 1/4. What is new on the next level is that these two things combine. So together we have 2/4 here, and only 1/4 and 1/4 here. On the next level, the same thing happens. This 1/4 is split into equal parts, and 2/4 are also split into 2/8 and 1/8 and 1/8, and we have combination. No, let me write here. It's 1/8, 3/8, 3/8, and 3/8. So there is some general rule how we fill the table. So if for example, let's imagine we look at this place. So imagine we have some, I don't know, x, and here with some y fraction. Here we have x over 2 and y over 2, and here we have x, the sum, and get x plus 1 over 2. So we assume that at each splitting the flow goes in two equal parts. Oh, this is the rule, so you can easily fill the table, and probably you see that this table is similar to a thing which you should know, Pascal triangle. So assuming that beans are divided evenly is this assumption about real world, but then after that we have mathematical computation, and this is the rule that we used, and this is the table that we got, and this table is just, you see, this is the power of 2, 1, 2, 4, 8, and these things are like in Pascal triangle. And this is Pascal triangle divided by powers of 2, and if you want to write a formula, it's like this. It's binomial coefficient. K is the number in the line, and 2 to the n is the number of the line itself. And this concentration effect now can be estimated quantitatively. You can just compute and see really if the model is correct, which fraction of the bean should be near the center, and it's you can find just a number. So I don't know, you can take 100 layers, then the beans are from 0 to 100. This k is from 0 to 100, and if you decide, for example, the center is between 40% and 60%, you can just compute with an easy program what fraction of this beans goes into the center part. And this, if you compute the same for 1,000 layers, it's also not very difficult for a computer. You need an array of size 1,000. You don't need to fill the entire table. You should just go from top, filling line by line. And if you do this, then you see what fraction is here. And you will see, I promise you, I don't remember the numbers, but I promise you that for this part, the concentration effect is much stronger. Almost all the beans will be near the center. So this is the same effect somehow that we observe with frequencies, but now it's not for one sequence. It's just we look on many, each individual bean somehow has some individual trajectory, and we count the number of trajectories going in different ending at different places. I want to say more things about the division of probability theory between natural science and mathematics. So if you ask some people on the street what is probability theory, maybe some of them will tell you that the probability theory says that the coin should get head and tail equally often. But actually, strictly speaking, it's not the case. Mathematical probability theory doesn't care about the coins at all. It's just a part of mathematics. And if somebody makes a coin which has 2 tails on both sides, of course this person will not destroy mathematical probability theory. And just a coin is bad, but theory is good. So again, let's see what is the separation line. So natural science care whether the real coin behave according to this equal head and tail model. And mathematics studies the implication of this model. For one coin tossing, it's not much to study, but still the mathematics starts with the model and then finds what are the consequences of this model. And of course, normally mathematicians work together with some other scientists. So if the model is not good, they found this and they try to suggest a different model and so on. But purely theoretical, there is a division like this. Let's look at some special case when this illustrates this division. So imagine we toss 2 coins, and for example, you can just take 2 coins and do something like this, and you see something. What do we see? Oh, now we see 2 tails, but their question which we want to ask is what is the probability to have 1 head and 1 tail? And just imagine a discussion. This question is asked, and then Alice says something like that there are 2 coins, so the first can be head and the second can be head, or first head, second tail, or first tail, second head, or 2 tails. So there are 4 outcomes, and we are interested in which fraction of this of the coin experiments, we will have one head and one tail. So if all 4 outcomes are equally probable, there are 2 of them which corresponds to one head and one tail. The probability is 2 of 4, so it's 1/2. This is what Ellis says. But now some other guy comes, Bob, and says, look, you see that why there are 4 outcomes. You have 2 coins, you toss them, and when you look, you don't know where is the first coin, where is the second coin. So essentially there are 3 outcomes, 2 heads, head plus tail, and 2 tails. And so if we assume that these 3 outcomes appear equally often, then the probability of this outcome is 1 of 3. And so who is right here? Then a pure mathematician, Charlie, comes and says, you are both correct. You just have different models. And I don't care about real coins, but if you want, you can assume, consider this model or that model, why not? They are just different assumptions. And of course, if you want to know what happens really, it's not the mathematicians who should be asked. We should ask some, I don't know, natural scientist or physicist, and he will tell you that indeed Ellis is more right. So for the real coins, just it's an experimental observation. These 4 outcomes are almost have the same probability. And so if we classify things according to Bob's scheme, this outcome will appear twice more often than this or this, because in this model there are 2 cases which corresponds to 1 case in this model. Again, so this is this distinction between mathematics and natural science. Let's look from this viewpoint on Galton board. What would we assume really? So one can say that the assumption is at each level, half of the beans go left and half go right. And it's, yeah, of course we assume this, but it's not all, because you can imagine, for example, if a board, just depending on the board construction, maybe the beans actually, when they make a first move, they get some velocity, and if they go to the left, then in the next move they will also go to the left, because they already have this direction. So maybe in the physical world it can happen that some decision on the level k influences the decision on the level k plus 1. As for example, going left makes the next left move more probable. But we assume our computation was based on the assumption this doesn't happen. So we assume that in probability theory language it's independence. We assume that among the beans that go left, if we consider only the beans that go left at level 1, half of them will go left at level 2 and half will go right at level 2. So the second decision is somehow independent from the first one. This was our assumption, and we made computation based on it. Now we switch to another experiment, which is rolling dice. So unfortunately I don't have a dice now, so I can only show you a picture, but probably you have seen it, so you can also toss it and roll it or roll it like this or whatever, and you can get a number which is between 1 and 6, 1, 2, 3, 4, 5, 6. So it's very useful if 6 people go in a restaurant and can decide who of them pays. And natural science part is that this 6 outcomes appear equally often. It's observation. And mathematics can make some conclusions, but of course what we will say, this is our trivial conclusion. So for example, we can conclude that even number 2, 4, 6 appears in 50% of cases, and a multiple of 3 or 6 appears just 1/3 of cases. Why? Because it's very easy. We have just 6 outcomes. It's 1, 2, 3, 4, 5, 6. And if we want to get an even number, among these 6 outcomes, there are 3 favorable outcomes, 2, 4, and 6. So we have 3 over 6, which is 50%. And for multiple of 3, we have 2 over 6, we have 2 favorable outcomes, 3 and 6, so we get 1/3. Trivial. What is not so trivial, it's what happens if we roll 2 dice. So imagine we have a red and blue dice, and then if we roll them, or if we do some other way, make them produce random numbers, then we get an outcome which is a red number and blue number. Each of them, for example, x is red and y is blue, and each of them is between 1 and 6. And how many of them do we have? Well, if you remember something from combinatorics part of the course, you will tell immediately that it's 36. And even if you don't remember, you can just write all 36 outcomes and believe that they are equiprobable. So this is a table. So red, you see this, for example, 4 on the red dice and 1 on the blue dice, or whatever. They are all possible combination. If you don't believe me, you can count all the numbers here and you get 36. And the assumption is that they all appear equally often in the real world. So if we assume this, we can compute the probability. So let me explain the language of probability theory. So there is something which is called probability space. It's just the set of all outcomes. So in our case, we have 36 outcomes and they form probability space. Also, there is some event, something, this is a property of outcome. It may happen or not. And it's a set of outcomes, and these outcomes are called favorable. That's what we want somehow. Of course, we can consider probability of undesirable events, so it will be an unfavorable account. But just this is a kind of language used. So if we have an event, we call the outcomes from this event favorable. So for example, imagine we have an event that the red number is bigger than blue number. And we want to compute the probability of this event. And probability is just the fraction of this outcomes in a long series. So if we believe that all 36 will appear with the same frequency, we just want, what we should do, we should compute the number of favorable outcomes and divide by 36. So where the red is bigger, red number is bigger. So here they are equal. So this is all this. No, I think I prepared a nice picture. Yeah, with boxes. So these boxes show favorable outcomes. And then you can count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And so we get 15 over 36. We know that favorable outcome will, in the long run, form 15 over 36 fraction. This is called the probability of the event. What is very important, that somehow we can, it's called independence. We assume that red and blue dice are independent. Let me explain what does it mean. So we have 36 outcomes and we believe that they appear equally often. So red dice can give 1, 2, 3, so there are this rows. We can have 1, 2, 3, 4, 5, 6. It's equally often. And also blue dice appears with 1, 2, 3, 4, 5, 6. And this is cases are equally often. But this is not only, it's very important things that they are also independent. For example, imagine some magic dice which always, for some strange reason, red and blue show the same thing. And then, of course, almost all the outcomes disappear. What we have is something like this. This is the only 6 possibilities. And these 6 possibilities are equiprobable. And then, indeed, the red dice is okay in isolation and blue is okay in isolation. But, of course, all our theory doesn't work because they are somehow dependent. That's the language of probability theory. We will return to this dependence question later. So independence is somehow more than its equiprobability for both dice. We assume that all 36 outcomes are the same, have the same frequency. And it actually happens in the real world for many settings. For example, you can toss the two, roll the two dice at the same time. Or another thing you can do is you can take, first you can roll the red one and then the blue one. Or even, you can do even more, you can take one dice and roll it twice. And first you get the red number and then you get the blue number. And in all three settings, actually, in fact, in the real world, all combinations will appear equally often. This is observation about the real world, but then we can compute the probabilities as we have done in our example. So you can, this is again the division, equiprobable model happens in the real world, and then mathematicians use it for computation of probabilities. Now we consider other examples of probability spaces. We will have more later, but just to illustrate the notions, let me show some. So first is a sequence of coin tosses. So imagine we toss a coin n times, when n is some probably large number. So what is then the outcome? We just write down heads and tails or zeros and ones. So the outcome is just a sequence of n bits which show the outcomes of first, second, and so on, coin tossings. And how many we can have of them? If you remember combinatorics, you know that it's 2 to the n. So each new bit increases the number of possibilities twice. So you had, in total, you have 2 to the n. And the assumption, which usually is used in probability theory, that all 2 to the n outcomes have the same probability, appear with the same frequency in a long series of experiments. And it's not so obvious really, because imagine we toss, I don't know, the coin 10 times, and one of the possible outcome is just 0, 0, 0, 10 zeros. And another one is something like, I don't know, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 2, 3, 4, 5, 1, 2, yeah. So this account, 10 zeros and this. So what do you think? Is which of them will appear more often? No, it's 10 zeros, so you should, the dots are for zeros only. So there are two specific outcomes, 10 zeros and this one. So which of one will appear more often in the real life? And you know, maybe some people believe probably that this is more probable because, you know, the zeros is something strange. You have white always zero, but actually the current understanding of the real world is that these two outcomes will appear equally often in the real world. But this is about real world, and mathematical assumption starts here. So we agree in advance before computing some probabilities that they are all the outcomes are equally probable, appear equally often. So for example, probability of all heads for n bits, it's just 1 over 2 to the n, when n is the number of coin tossing, and we have 2 to the n outcomes, and we are interested in the one account. You can consider more interesting events. Imagine that event is the first bit is equal to the last bit. So for example, this event happens if we start with 0 and end with 0, and also happens when we start with 0 and start with 1, sorry, and end with 1. So what is the probability of this event? What do you think? Actually, it's easy to think that it's 1/2. Why? Because there are actually 4 possible groups. You can have 0, 0, 1, 1, 0, 1, and 1, 0. And here in all 4 groups, you have arbitrary n minus 2 bits. So this 4, we divide all the outcomes into 4 groups, and these 4 groups A, B, C, D, have the same number of outcomes. So each of them is 1/4 of all possible outcomes. So our groups here is just 1/2 together, it's 2/4. So this event has probability 1/2. Or if you remember combinatorics part, probably you will remember computation like this. And then another question. So for this is probability 1/2. Another question, more difficult, and I will not tell the answer, so you can think about it. So the event is that number of heads is even. So if we sum all the zeros and ones, we just have a number, or I don't know, remember, maybe it's number of tails. Anyway, it doesn't matter. So the number of heads is even. What is the probability of this event? Oh, I will tell you the answer 1/2. Yeah, it's 1/2. But what I won't tell you is why it's 1/2. But maybe you remember something from combinatorics and you can see it immediately. If not, think a bit and you will get, I hope you will get the idea why it happens. Again, we can also look at Galton board, and here the outcomes are very similar. It's a sequences of not zeros and ones and heads and tails, just left and right. Of course, you can use any notation. And again, we have 2 to the n outcomes, and the probability space is made of all these outcomes. And if we are interested, they are assumed to be equiprobable. And if we are interested in the concentration event, if we want to compute the probability that the bean will end in the middle, we just consider the event that the number of r's in the sequence is between 40% of n or 60% of a total number. And so this is an event, so we need to compute how many outcomes are in this event and divide by the total number of outcomes. So according to general formula, favorable outcomes are just the outcomes where the number of r's is between 40% and 60%. And so this is the formula, it's the same formula you have seen. This is the number of outcomes with exactly k letters r, and then we make a sum and divide this sum by 2 to the n, and that's what we wanted. So now you probably will say that why should we learn probability theory? It's just combinatorics in disguise. You can ask about probability of something, or you can just ask about the number of outcomes. And this is essentially the same question in different language. And it's true, and it's mostly true in our course, but it's not completely true in general. So first we speak only about mathematical part. So there is also a question of natural science, which models are good or bad, but we decided it's not probability theory, so for us we consider the mathematical part. And mathematical, still there are important things. So probability theory cares a lot about this independence thing. And in combinatorics, we usually don't speak about independence. We just count things. So if we concentrate on whether some events are independent or not, this is more about probability theory. Also, if we are interested in finding model for real world, for example, a coin may be non-symmetric, or dice can be could be one part could be heavier. So then, of course, not our assumption that all the outcomes 1, 2, 3, 4, 5, 6 are appear equally often is wrong. So we should somehow consider another models which are called non-uniform distribution. We will speak about this. And sometimes we don't know, we want to speak about probabilities of different events, even if we don't know exactly the underlying distribution. So the simplest example, imagine that some event A has some probability. So then we consider the negation of A, the event saying that A didn't happen. And what is the probability of this negation? Of course, negation happens in cases when our event doesn't happen. So it's just the complement. So the probability is 1 minus probability of the event. And for saying this, we don't need to know anything about underlying distribution. And finally, there is a part of probability theory, very important, which we completely ignore in our course. It's about continuous distribution. Let me just say one thing. So imagine, I don't know, there is a rain outside, and you go with a piece of paper and you see where the first drop falls, and it can fall at any position. But you are interested in cases when it falls into some region. You draw a picture on this paper, and you see whether it goes inside the figure or outside. And of course, then outcomes are not. There are infinitely many of them. The drop can go in any point on the paper, so you cannot count them. But what you do instead, you just look at the area of this thing, and the empirical fact is that the fraction of cases when it goes inside the zone is proportional to the area of the zone. So it's kind of, mathematicians say, measure for areas and other similar things. So the probability theory is a part of measure theory, and a part which deals a lot with independence. But it's a complicated thing. You need to know the notion of integral. So we will not go into this and consider only discrete distribution when the number of outcomes is finite. Now we start to discuss the limitations of probability theory, what is possible to do and what is not possible to do. So let's start. First thing is just the notion of finite probability space where not all outcomes are equiprobable. And you know, the equiprobable outcomes are more for exercises in textbook on probability theory than in real life. Most probability theory is not applied to dice or to coins. And even a real dice may be asymmetric. If a coin can have one side could be more heavy and fall more often. But this makes the frequencies of different outcomes different. But this is not a problem as soon as this frequency still stabilize around some value. So if we have a long series of experiments, then we should have some limit values of frequencies, or which could be called probabilities. And then, for example, if we know that for a dice there are some limit frequencies, P1, P2, P3, and so on, and we want to know how often the even number would appear. It's a combination of three cases, of 2, of 4, and of 6. So we should add these three numbers to get the probability of an even number. So here is the formula. And then you can be sure that in a long series, if the individual outcomes will have stable frequencies around the probabilities, then this combined event will also have the required stable frequency. And the last thing which you should know, that if the frequency of individual outcome, the stable frequencies should give some 1, because it's at each stage is the case. So if things stabilize, it will be also the case after the stabilization. Okay, now we can give there is a special slide for a formal definition of finite probability space. So let's look at it. We have a finite set of outcomes, and each outcome has some probability. It's a number, a real number, which should be non-negative, and the sum should be 1. So all the numbers should be between 0 and 1, therefore. And we know what is an outcome, and event is just a set of outcomes. Any set of outcomes is considered as an event, and the probability of this event is defined as the sum of probabilities of outcomes that form this event. Just what was in our example, but in a general setting. Last small technical details, whether some pi could be 0. It's not that important. We allow this formally, but these outcomes actually, if they have 0 probability, they can be ignored, and we just can delete them from the probability space and get essentially the same probability space. So here is the formal definition. And now we look at an example. I prepared an example. So here is the probability space X. It consists of 6 outcomes 1, 2, 3, 4, 5, 6. And they have individual probability, P1, P2, P3, P4, P5, P6. And if we have some, the sum should be 1. Here it's written. And if we have some event, now here is this event A, it consists of 1, 2, and 3. And its probability is the sum of probabilities of these events. Probability of A is the sum of individual probabilities, as we have said. And if we have another event B, then it's now made of 5 and 6, and there's probability P5 and P6. Of course, the probability is just the sum of P5 and P6. And now we can consider the combined event. In set theory, we say the union. In logical terms, is the event A or B. So it happens when A happens or B happens. In our case, it's not possible together, but just A or B is 1, 2, 3, 5, 6. And of course, the probability of this event is just the sum of these probabilities, 1, 2, 3, 5, 6, and they can be split into two groups. In probability of A is one group, and probability of B is another group. So we have this formula, and we will see this formula in the general case a bit later. Now let's speak more about finite spaces, and let's start with what we finished with, is what is called the mutual exclusive event and the formula for the probability of some probabilities. So the event is a set of outcomes, and the mutual exclusive event are just this joint set of outcomes. But there is an important thing. So imagine somebody asks you, I toss a coin and get, I don't know, head. And another time I roll a dice and get 3. So are these outcome events, are they mutually exclusive? And the correct answer is not yes or no. The correct answer is that they are not defined on the same probability space. So the question has no meaning. It's often the case in probability theory when the question has no meaning. Anyway, if there are two mutually exclusive events, then the probability of their union, A or B, is the sum of probabilities. That's what we have seen for a specific example, and this will happen in the general case as well. A special case of this rule is when this mutual exclusive event are complementary. So imagine we have some event A. Then it defines another event which is called not A. This event happens when A doesn't happen. In terms of set theory, it's the complement of the set which form the event. And A and not A are mutually exclusive events, and together they can cover the entire space. So the sum of probabilities should be 1. So the probability of not A is 1 minus probability of A. So if you believe that probability, I don't know, to see a crocodile is 1/3 for whatever reason, then you should agree that the probability not to see it is 2/3 at the same experiment. Okay, there is no reasonable probability space here, but okay, just it's a simple rule. This is the explanation why it happens, because they are mutually exclusive, so we can apply the sum rule. And the last thing we want to discuss about these two events, what if they are not mutually exclusive? So then this probability of A or B is maybe not equal to sum of probabilities. But now the question is it bigger or smaller? What do you think? And let's see an example, and we will see the answer immediately. So imagine we have two events A and B, and they are not mutually exclusive. There is some outcome 3 in both. And then probability of A is P1 plus P2 plus P3, and the probability of B is P3 plus P4. Now there is common P3 here. So if we look at the union A or B, it's just P1, P2, P3, and P4. And if we add these two probabilities, look, we will count P3 twice. So to get the correct answer, we should compensate and subtract this intersection of these events, which is now only 1 P3. And this rule, probably you see this, you have seen this in combinatorics, it's inclusion and exclusion formula. And it's true for general probability spaces also, not only for the equiprobable outcomes. Another story, when a finite probability space with non-equal probability of outcomes appears, it's what is called sequential choice. Let me explain. So there is some prepared example. The question is how to select a reasonable probability model for some experiment, and the experiment is like this. We have 6 balls, 1, 2, 3, 4, 5, 6, and we have 2 boxes. And the balls 1 and 2 are in one box, and 3, 4, 5, 6 is in another box. And then the probability experiment is described as we choose a random box and then choose a random ball in the box. So the question is, what probability space reasonably corresponds to this process? And what we assume that the boxes have equal chances to be selected, and in each box all the balls have equal chances to be selected. And we want to decide what are the probabilities of all 6 outcomes. Probably you can say the answer immediately, but still I prepared some slides to explain this, so just keep it if it's obvious. But it's useful to represent what is happening as in a kind of a tree. So we have a tree, and this is the first choice, whether we take box 1 or box 2. And here we made the second choice, when we take one ball, either 1 or 2 if it's box 1, or 3, 4, 5, 6 if it's box 2. So in half of the cases we will go left, in half of the cases we'll go right, because the boxes are equiprobable. And here then we can go in half of this half we go here, and half of this half we go here, and here we have one of the 8 things. So this is how we get the probabilities for 6 outcomes. And using the fact that at each point all choices, all further choices are equiprobable. And then is another explanation. So here is just the event we select box 1, and here is the event we select box 2, and they should have probability 1/2. And also this individual probability inside the boxes should be also equal. So there is only one possibility for that, and that's written here. It's exactly the same numbers, but explained in a bit different way. In this part, we have some puzzle, or I don't know, some tale. And the tale is about a prisoner and a king. So the king calls the prisoner and tells that look, here we have 15 white balls and 15 black balls, and these balls will be used to determine your fate. Oh, the king can determine the fate of everybody. And what the prisoner can do? The prisoner is allowed to put the balls in the boxes in any proportion. So each box should be non-empty, but he is able to put black and white balls as he wishes. And then king promised that he will choose one of the boxes randomly, and then take a random ball from this box. And if this ball is white, then the prisoner is set free. And if it's black, something bad happens. So imagine that prisoner wants to increase his chances to be set free. And he wants to be free, and there is no cheating. The prisoner cannot just throw away all the black balls, or the king cannot kill the prisoner even though the ball is white. So everybody follows the protocol, but still the prisoner should maximize the probability of being set free. What should the prisoner do? And here is the answer. The answer is that you should have one white in one box. Prisoner should put just one white ball, and in the other box he should put the rest of white balls, 14 white balls, and all the black balls, 15. So what does it give? So if the king took the box with only one white ball, then the prisoner is guaranteed to be free. But if the king selects another box, then still the prisoner has some reasonable chances. It's just a bit smaller than 1 to 1. It's 14 to 15 because there are only 14 white and 15 black. So it's a bit less, in total it's a bit less than 3/4. But I claim that this is optimal, and it's not very easy. It's somehow obvious if you think intuitively obvious. But mathematical proof is not so trivial. And I will not explain it completely formally with all the formulas, but it's a really valid mathematical proof, just explained in an informal way. So you can think about it and you can try to retell it in a more formal way if you feel it's necessary. Okay, so now the proof. It should be prepared. Yeah. So actually the prisoner has somehow two-dimensional space of choices. So he should decide. No, it's not just we describe this choices this way. So first he decides how many balls will be in the one box and how many balls will be in the other box, ignoring the colors. So first he decides just the numbers, and then so this is the splitting of 30 balls into two boxes. And second, he decided how the colors are distributed. So how many black balls we have in the first box and in the second box. So this is the second decision. After the total number is fixed, the prisoner can modify the numbers, but he should balance things. So the total number should be as prescribed. So let's look at the second stage, when the proportion between boxes is fixed. And this is the most important informal, but which can be made formal, but informal remark, that the color of the ball is more important in the box when there are fewer balls. So if it's a small ball, look, imagine you have a small box and a big box. No, a box with small number of balls and big number of balls. So, and then you can vary the change the number of black balls and white balls. So you can add, you can make one black ball white in a small box, but you have to pay and make one white ball black in the big box. But the increase in probability in the small box is more important because the denominator is smaller. So if the total number of balls is smaller, then each ball means more. And for box with a large number, it means less. So we use a strange C notation just for fun. So this means that in small box, the number of white balls is we increase by 1, and the number of black balls we decrease to keep the total number the same. And here to compensate in the bigger box with bigger number of balls, we should decrease the number of whites by 1. And what I'm saying is that is profitable, because in the smaller box the number each ball costs more, so to say. And so we can do this, repeat this, until we have all the white, all the balls in the small box are white now. And it's enough white balls because it's smaller box, so at most 15. Okay, so we see that the situation can be improved. Whatever we start with, we can improve the situation by adding, making balls in the small box white. But then, imagine we continue this until it's possible. When we finish with all white balls in the small box. But then, it's easy to observe that we don't need that many. So 1 is enough, it's still probability 1. And still the other balls can be used to increase our chances for the other box. So we get exactly the same, the answer we claimed. So in the small box we have 1 white ball, and all the rest, all the white balls remaining and all the black balls are in the other box. Just exactly what we said. There is a small technical detail that when we say small and big box here, we assume that we implicitly forgot the case when they are equal. But then, of course, if they are equal, then this first stage doesn't change, doesn't make things better, but also doesn't make them worse. So we can do it anyway, and then we came again to this case. So this case can be obtained from any other, and so its optimization ends here, so it's optimal. You can complain that I am telling more what you should not do after hearing this section, but it's very important, because the most danger of probability theory is not that you cannot compute something. The danger happens if you believe that you have computed something and this is wrong, and you make a wrong decision thinking that it's based on probability theory. So let me say something about what you should not do. The first thing you should be very careful is the probability of the past events in the past. So I looked to get an example, I looked, just Googled for some historical statement, and that's what I found. It's from actual historical paper, and it says it's quite probable that in 12th century something happened. And but okay, you can say that it's quite probable, but if it's not mathematical probability. If the other guy asks, what do you think, is the probability greater than 2/3 or smaller than 2/3? Probably this has no meaning, because 2/3 means that if we repeat the experiment many times, in 2/3 of cases we will get something. But you cannot repeat the experiment. So the numerical value for this probability is something very strange. You should avoid this. Another example, more clear. So imagine I ask you, what is the probability that I have a dollar bill in my pocket? And you may start to guess this, but it's not the correct thing to do, because it's not, I either have it or I don't have it. And it's not clear what the probability could mean. There is no, if each day I come with the dollar bill or without the dollar bill, you can compute the fraction of the days when I come with it. But in one isolated case, the question has no meaning. Oh, we will see later something when it still can have a meaning, but a different meaning. Okay. There is one very clear example of this case, and it's a rather practical one, so let me tell you. So you know that first, prime number. Prime number is a number that cannot be factored. So I don't know, 5 is a prime, but 6 is not, because it's 2 times 3. So a prime number, you cannot factor it. And big prime numbers are rather important, because we will see this later. They are used for cryptography. For cryptography, you take 2 large big prime numbers, you multiply them, and nobody can factor back. But anyway, you need the big prime numbers, and there are algorithms which are used to decide whether a number is really prime or not. But the fastest algorithms are randomized. What does it mean? The algorithm uses some internal coin. It's not a coin actually, it's some other physical device or some prepared random bits. But the answer of the algorithm depends on these values of these random bits. So if we apply this algorithm many times to some number, then it can give different answer. And there is a proportion of correct answer. And if you write a good algorithm, you can prove, for example, that for whatever number you take, if you repeat the same algorithm on the same number but with different random bits, you will get answers, different answers, but most of them will be correct. The probability of wrong answer is, say, less than 1%. Okay, this is perfectly good statement. What is not good if you say something like this. So imagine you tried this algorithm for some number. So I choose some number which was actually, people don't know whether it's prime, so they try this randomized algorithm. So imagine you tried your good algorithm on this number, and the algorithm says that it's prime, as it did for this number. And then you say that, look, this number is prime with probability at least 99%. But this is complete nonsense. This number is either prime or composite. It's not prime with any probability. So you should avoid such a statement, and you should see when somebody else makes such a statement, and you should be very careful about the knowledge of probability for this guy who says this. This you should not do. Now let me say a few words about what probability theory, how it can be extended. And first the simple thing which I already have said, that is infinite probability spaces. So for example, the meaningful setting, if for example we want to take a random natural number and we agree that 0 should appear with probability 1/2, 1 with probability 1/4, and 2 with probability 1/8, and so on. So it's even easy to imagine an experiment which produced this. So for example, you can toss a coin and count the heads before the first tail. So you say 0 if you get a tail immediately. You say 1 if it's head, tail, and something. You stop coin tossing here, but anyway. If it's 2, this is 2 heads before tail. And the probabilities are exactly 1/2, 1/4, 1/8, and so on. So it's kind of a reasonable thing to consider such a space. But if somebody says that take a random integer and make all of them equally probable, then you should immediately complain, and this has no meaning, because if they're equally probable, then what is this probability? If it's positive, then the sum becomes bigger than 1 for a large enough initial segment. So the probability should be 0, and if all probabilities are 0, what does it mean? So equiprobable integers is something impossible. Okay, this is the first remark, and the second case we also mentioned. And when we can find a random point in a square if you go on the street and wait until a drop falls somewhere, and it's reasonably to believe that it's a random point in a square, and the probability to get it inside some zone is proportional to the area of the zone, and so on. So infinite probability space are dangerous, but not that dangerous. In many cases, it's a reasonable thing. And another thing which somehow even the probability of individual event, which I told you that you should not consider, sometimes they can be considered in a different economic sense, so to say. So imagine that we want to ask what is the probability of some guy, politician X, to be re-elected. And you can say that probability is 80%. What does it mean? Of course, you cannot repeat the experiment. You don't have many worlds with the same guy in each of them and see how many of them, in which proportion are the worlds when he's re-elected. And so it looks like something stupid and non-existent. But still, imagine that some people don't like this guy to be re-elected, and they want some insurance. The insurance is just a paper that guarantees you that if he's re-elected, the insurance company will pay you, I don't know, $1 or any other amount, but let it be $1. And the question is the market price of this insurance paper now. So if there is a market for such a thing, and if the selling price is close to buying price, then you can say that if it's, for example, around $0.8, then you can say the probability of being re-elected is 80%. Of course, it has no statistical meaning, but still this number obeys some rules of probability theory. And you can even somehow prove the sum rule for disjoint events. So for example, if you want to consider the probability of A being elected and B being elected, and the probability of A or B being elected, and there is some reason why the insurance paper for all three cases should have matching probabilities. The last one should be the sum of the previous two. So I will not tell you why it's the case, but you can think about this and you will guess why it happens. So if the problem with my pocket and the dollar in it, no, there is no dollar actually. The problem with this insurance is that nobody will sell or buy insurance on this, so there is no market. But for more important event, there is a market, and if there is a market, actually you can bet. In some countries it's legal. You can bet for political events, so there is a market, and this market can be considered as a definition. The market price can be considered as a definition of probability for individual events, and then we also get somehow a probability space, even if there is no repeatable experiment there. So now we switch to a topic which somehow is central in probability theory, which is distinguishing from measure theory or combinatorics, the conditional probabilities and independence. So first, conditional probability, and I want to start with some example, which just some kind of demographic example, which has nothing to do with probability theory. I just want to illustrate the language, probability theory language, by comparing this, by retelling the same story both in normal language and probability theory language. So let me explain. So this is just statistical data taken from Wikipedia. If you look at United States population, then and you look how many people are of age 65 or over 65, then it's 14%. And sometimes you can say in language of probability theory that for a random American, the probability to be of age 65 or bigger is 0.14. Of course, it's rather strange. How do you select a random American? Somebody comes and picks a random American mystically. And it's a real problem if you make a statistical a poll. You would like to select a random American, but there is no procedure which does this, so it's a big problem for pollsters. Anyway, we agree on this 14%, but now we look at the male-female ratio for age 65 in this group, 65 and over. And actually the women have bigger life expectancy, so there are significantly more of them. It's 3 to 4. So 3 to 4 is just 3 out of 7, and it's about 43%. And so among these 14 persons, there is 43% of male in this group only. And we can, just if we want to compute the total, in total how many we have males over 65, then we can compute this by, first we take the 14% of old people, and then the fraction of males among the old people, and we get something like 6%. Of course, it's not exact computation, but the data are just approximate, I guess. Okay, so this is all trivial, but then this trivial thing can be explained in the language of probability theory. And first thing we have said, this 0.16 is the probability for a random American, this mystical random American, to be at least 65 years old. And now what is important, then the fraction of males among the people who are of age 64 or more is called conditional probability, the conditional probability of being male under the condition that you are at least 65 years old. So there is a condition, and there is the event of being male, and you look at the conditional probability of this event. So it's a fraction inside some group. And you can use this, if you know this fraction and you know this fraction, you can compute the total probability of being at least 65 years old and male. That's not total, just probability of this combined event. And this is the product of these two probabilities. So I write it again. So probability of being male and at least 65 is a product. First, the probability to be at least 65 is for 14%. And the conditional probability of being male with the condition that you are 65 or older, it's here. And this is 43%. So in product is 6% approximately. So this is the same computation but repeated in probabilistic terms. And general statement, the probability of A and B is just the product of probabilities of B and conditional probability of A given B. And actually it's just a definition of conditional probability. So we will see this definition in the next example more close to our standard probability theory things. So now we have probability space with 6 equiprobable outcomes, 1, 2, 3, 4, 5, 6, and A is at least event at least 3. So there are four outcomes here. And B is the event to be even. So inside this event, not inside this event, this is A, and the B is this. So somehow, so this is B. And now we can consider all these things conditional probabilities for this special case. So A and B is to be this by definition. First we consider the conjunction, the end event. So A and B is just the even number which is at least 3. And there are 2 of them, 4 and 6. And so if we want this product, so we can say the product of being even at least 3 is a product of being at least 3 times the product of being even under the condition that you are at least 3. So just the probability of being at least 3 is 4 out of 6. And out of this 4, there are A and B. There are only 2 of this 4. So we get 2 of this 4. And the product is, of course, 2 out of 6. 2 out of 6, so it's the probability of being A and B together, trivial. Yeah, here is this 1/3 is the product of this 2 things, 4 out of 6 and 2 out of 4, as I have said. Again, the conditional probability is a fraction of B outcomes among A outcomes. So it's in the picture you have event, so you have the entire space, you have event A, you have event B, and now you look only inside A, so B forms some fraction, and you look how big this part is inside A. So this is conditional probability, and this is for equiprobable outcome. You can just count the numbers, and you can, in general case, you can just define by this equation. This is a ratio. This is definition of conditional probability. In this part, we consider a somehow counterintuitive test example which is related to conditional probability, just a test and disease example. So let me explain what I mean. So imagine there is some disease which is not very rare but rather rare. 1% of all people in some population have this disease. And you have a test for this disease, and every test can give false positive and false negative. So false negative, the test is negative while you are ill, and false positive is that the test is positive if you are not ill. So the rate means that 1/10 of all people who have the disease get negative test. No, it's not, so it's somehow 90% reliable, so to say. And also the false positive rate is equally small. If you are positive, then 90%, if you are not ill, then the probability to get a false positive test is 1/10. So again, 90% people have are classified correctly. And imagine that now you are informed that your test is positive. And the question is, how much should you be worried? Of course you should be, but what is the probability that you are really ill? So in terms of our probability theory, we can say like this. So the probability of the disease is 1/100, and the conditional probability of test, if you really have the disease, is 90%. So this is false negative, so to say false negative if the test doesn't show you. So this is the complement. And here is false positive. You are not ill, but you have a positive test, and this happens with probability 1/10. Okay. And this is what is given. And the question is, what is the conditional probability of having a disease under the condition that you are test positive. So you can stop here and think, what do you think? Is it high or not? I think that many people will say that, look, test is quite reliable, 90%, it's almost, in all the, most of the cases, it's correct. So most probably I have the disease. Many people will think so. But it's a wrong understanding. So you should, before going into panic, it's a good idea, before going into panic, you should think a bit and compute a bit, and then you understand the situation better. So let me tell you what I mean. So just we compute things slowly. So there is 1% of ill people here. And 90% of these ill people are positive. So it's 90% of 1%, so it's just 0.9%. Positive and ill. But also there is 99% of healthy people. And some of them are also positive, just 1/10 of them are test positive. So there are 10% of this. And so we have 9.9% in the population of people who are positive but healthy. And now you already see that positive and ill is much smaller than positive and healthy. So it's just in proportion 1 to 11. So if you look at all positive people and find one of every 12 positive people, 1 is really ill and 11 is healthy. So it's not so bad. Only the probability to be ill, assuming you are test positive, is 1/12. And the same computation can be done in terms of probability theory. Let me repeat it slowly again. So here is what we start with: the probability of the disease, the conditional probability of positive tests, and if disease happens, and the probability of test if the disease doesn't happen. And this is what is given. So that's what we want to compute, and now we make the computation. So first we start probability test and disease, and the formula is we multiply the probability of disease by the conditional probability, and so we get this, and this is 9 out of 1,000. And if you compare this with test and not disease, test and healthy, we also do the same. We have 99% of people who have no disease, not this disease, and among them there is 1/10 who are test positive. So we get this number. And then we can just compute the probability of being positive. It's just the two disjoint cases, so the sum of probabilities works, and we can just add these two numbers and get this sum. And now we can just compute the conditional probability according to the definition. So the probability that you have disease under the condition you are test positive is by definition a fraction, a ratio of these two probabilities, and you know both of them. This is this one, and this is this one. So you divide this, and you get 1/12 as before. Of course, as before, we do the same. So it's like 8.3%. And it's not so big. So this is counterintuitive, but now probably it's not so strange as before. Let me say we used in this computation, we used something which has a serious name, the law of total probability, but actually it's a trivial thing. And imagine the probability space is split into some subsets, disjoint subsets which form the entire space. So they are mutually exclusive and exhaustive list of cases. B1, B2, and so on, Bn. So there are n events, they are mutually exclusive, and always one and in every outcome belongs to one and only one of them. I think there is, in language of set theory, mutually exclusive events. And then if we, let me draw something. So the entire space is split into this events. And then we have A some subset. And it also is split into events, smaller events here, which are A and B1. So this is B1, this is A and B1, B2, A and B2, and so on. So our A is split into mutually exclusive events, so we can compute the probability of A as a sum. Probability of A is the sum of the probability of these individual events, A and B1, A and B2, and so on. And each of them can be computed according to the definition of conditional probability, like this. So this, for example, is the product of B1, probability of B1, and the probability of A under the condition B1. And so on. We just get this formula, and this formula is called the law of total probability. And for the case when we have this B1 and B2, only two events, we have somehow B and not B. Here is what is the same. It's probability of B times the conditional probability. This is probability of not B, and this is the conditional probability. So we have just a special case. That's what we did actually in our computation. We apply this law of total probability in the case when we have only two. Now we start considering some very famous thing which is called Bayes' theorem. Actually, like other things we discuss now, it's something trivial, but it's very popular and very important philosophically. It's how I somehow say something about the reasoning, what kind of probabilistic reasoning is good. So there is a special name, Bayesian statistic or Bayesian argument or whatever. But the formula is very simple. Let's go to it. But still, I want to start with a real life example. It's real. Actually, several weeks ago, when I prepared the slide, I looked in my mail and I found that I have a message from Bank of America. But strangely, this message has an address in Japan. You see, this is Japan. And I thought that it's probably a scam. And why? What are the reasons for that? And the reasons are following. First, I know by experience that many scam messages have foreign address. So because this people who don't want to be caught, so it's convenient for them to use their address in a foreign country. So it makes the search for who really used this address more difficult. Anyway, it's just observation. Another observation, just in general, if we look at all messages, these foreign addresses are not so common things. It's not often, it's some clear contradiction between the place when the message comes, the name of the person and the location of the person and the address. And another third observation, unfortunate, that the scam messages are rather often. So people try to somehow to prevent them or to prosecute the people who send them, but still they are quite often, unfortunately. And these three reasons are just three components of Bayesian reasoning. I will try to explain what do I mean in the next slide. Yeah, so there are three components of Bayes reasoning. And here is the formula. So it deals with two events. They are called hypothesis and evidence, but just any two events are okay, just the names are this. But of course they should be in the same probability space. So for example, we can consider the event H and E. So recall the definition of conditional probability. So the conditional probability of H under the condition E, a probability of hypothesis, it's somehow counterintuitive. It's probability of hypothesis under the condition that event happens. Is by definition is just a fraction of they together divided by probability of the condition. And then we can use the same formula, the definition of conditional probability, in other direction. We can start with H and use the other conditional probability. You see that it's in different ordering. Okay, so what? we can rewrite it even like this. And it's trivial computation, but it has some meaning. And the meaning is can be explained like this. So we are comparing the probability of H with condition E or without this condition. And with condition E, somehow it multiplies the probability without the condition by some factor. And this factor shows how much E becomes more probable if we add the condition H. So the condition multiplies probability by some factor which is another ratio. So it's kind of explanation of this factor. We'll see this in an example. So let's compare our theory and our practice, our example with this email. So this is the bias formula. And what is the interpretation? So H, the hypothesis, is that the message is a scam. And the observed event is that message uses a foreign address. So how probable is that the message is a scam, assuming that it has a foreign address? And my reasoning was that this probability is rather high because first, this thing is quite high, which means that many scam messages use foreign address. And this is pretty low, that not many messages in general have foreign address. And this is not very low. Nowadays, there is a lot of scam. So we have, this is rather high, this is low, and this is not very low. So I conclude that the entire thing is high, and this was the reasoning why I decided that this is a scam. So I tried to write this, just in one sentence, the reasoning is written here. So foreign address makes the scam hypothesis much more probable compared to original probability, because it appears in scam messages much more often than in general. So this is a reading of bias formula for our special case. And let's now look on our example with disease when somehow similar reasoning doesn't work, why the formula doesn't give things. So again, we have a disease and test, the probability of disease for test positive people. And then we have this computation. So probability of test for people having the disease is 0.9. The probability of having the positive test, and we computed using the formula of total probability, and this is this. And here is the probability of the disease. And we get, when we compute things, we get only 8%. So why don't we get such a serious, a big number? And indeed, what can be said, that this probability of tests for people having the disease is much bigger than the probability than in the general population. But this probability of the disease is small, very small. So even the product is not very large, it's only 1/12 actually. So here the hypothesis was so improbable by itself that even the increase in the probability because of the Bayes theorem doesn't make it very probable. This is what happens in our example. Okay, Coursera wants all the time wants to have a take-home messages and repeating the main thing you should is learning objective. Okay, so here the learning objective is to understand the meaning of Bayes formula and see the cases when you apply this reasoning in the real life. So this is the message. If some conditions significantly increase the probability of some event by some big factor k, or of course it's true for any factor, but just if it's interesting for big factors. So if condition B increases the probability of A, then symmetrically condition A increases the probability of B by the same factor. So this is take-home message from Mr. Bayes. Now we want to consider a paradox, A paradox happens when there are two different arguments which give different answer, and there is a kind of a conflict between reasonings, two different way of reasoning. So this is a known, its paradox is known in the setting with children, but so imagine some woman has two children, and you know that at least one of them is a girl. So what is the probability for the other, that there are two girls, the other child, she has two daughters? Okay, this is a biological question, and whether they're dependent, the sex of the two siblings is dependent or not. But just to ignore this problem, let's consider the cleaned formulation without any biological information. So Mary just make it two times she tosses a coin, and it's known that at least one of outcomes is a tail, yeah. And so what is the probability to have two tails? And I will show you two arguments which give different answer. The first argument, first solution. Of course, if there is one of the outcomes is a tail, then there are two cases. Either the first bit is a tail or a second bit is a tail. And of course, these cases are completely symmetric, so we can consider one of them. We may assume without loss of generality that it was the first case. For example, first bit is a tail. And then there are two possible outcomes, tail head and tail tail. And this is the favorable outcomes when we have two tails. So there are two outcomes, equiprobable, and one of them is favorable, so the probability is 1/2. So are you convinced? What do you think? Let me show you another solution. It's more formal without this loss of generality stories. Here is again the question. And now we just consider 4 equiprobable outcomes. Head, 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 tail, tail, head, tail, tail. And just do the boring thing. We just look at all the events. So event, here this event, C, at least one tail. Where is it? It's here, here, and here. So it's probability 3/4. And this event, probability of 2 tails, is just this one. So among the 3 events, we have only one. Event E is 2 tails, it's only one outcome and probability 1/4. And actually, it's now easy to compute the conditional probability. Here is it. So we divide this 1/4 over 3/4 is 1/3. Or we can say that the condition is this and event is this. Now event is a part of the condition. So out of 3 possible outcomes, our event selects 1, so it's 1/3. So what do you think? Which argument is correct? Well, actually, the second one is correct. And to understand what is the error in the first argument, we should look at a picture. And first we should read the problem statement and parse the problem statement, so to say. So here it's shown in colors. I prepared this slide. So it's just the same statement, but there are 3 parts. The blue one, this one, yellow one, and the red one, or magenta one. Okay. What is the role of these 3 parts? The first part is just sets the probability space. Mary tossed a fair coin twice means that there are 4 outcomes and they are equiprobable. Oh, this is not said explicitly, but if you are in probability theory textbook, you always assume this, if it's not said, even if it's not said explicitly. And then here is the condition. At least one of the outcome is a tail. So it's a condition which is event made of 3 outcomes. And the probability of this event is 3/4. Here it is. There's 3 outcomes and probability. And so there is a space, the condition, and now the event we are interested in. So event E is 2 tails, and this is part of the C. And this has probability 1/4. And the conditional probability is 1/3. So I just repeated the second argument, but the only difference is that I clearly separated here the setting of the probability space and the condition. So it's, when you read this, it's not clear just Mary tossed a coin and list of the one of the outcomes, like kind of story. But if you want to ask a probability question, you should clearly distinguish the probability space and the condition. And actually it was the source of many errors. I think that just in 19th century people do not understand this clearly, and this was a source of many paradoxes and so on. But hopefully now people are better in this. And we can look at the first solution, wrong solution, what we really did there. And there is a picture. This is a picture for the correct solution. We have the space, this blue one, things, condition, this olive one, and event, this is event. So what we did in the first solution, we consider two other events, C prime and C double prime. And this is the event in the second tail, and this is the first tail. Or maybe they should be denoted in the other way. But anyway, there are two events, and together they make the condition C. But, for each of them, the conditional probability is different. It's 1/2. And for the entire condition, it's 1/3. So when we say without loss of generality, we do a very bad thing. We replace this by this only because this event C is a union of these two symmetric events C prime and C double prime. But for each of them, the conditional probability is different, so you cannot replace this. And kind of take-home message that information is not always you should distinguish between information which explains the space and the condition which is part of the problem. So you first you should explain what the probability space is, and then you say the condition and the event, and then the problem is set. And if you just make some kind of a story, it always it's a very easy way to get into trouble. You should avoid this and be clear. It is about informal questions. How can the past influence the future? But okay, it's very philosophical. Let me be more clear. So imagine that you have a dice and you roll it twice, and you are asked how probable is 6. And imagine you have seen 6 in the first experiment. And does this observation, does it increase, decrease, or doesn't leaves unchanged the probability of getting 6 in the second experiment? So in our mathematical setting, we can compute it easily. So here, the space is just a pair of x and y. Inside x is in 1/6, and y is also between 1 and 6. And all combinations have the same probability. And so we can compute the conditional probability of y equals to 6 under the condition that x is equal to 6 and without the conditions. And it's easy to do this, and both are 1/6. There are 36 equiprobable outcomes, and here we have only one outcome. So there's a fraction. So here we have only one outcome out of 36, and here we have 6 outcomes for all possible values of y. So we get 1/6, and this is also 6/36 because there are 6 possible values of x. So in our model, the condition doesn't change the probability. But model is model and real world is real world. So imagine there is a movie, Rosencrantz and Guildenstern are dead, I think it's called. And this movie starts with a long scene when one of these two guys make a coin tossing at many times, and it sees that it's always head, or maybe tail, but just the same result many times, and he becomes worried while the other guy ignores this problem. And so, but anyway, imagine you watch this movie and you see that it's head, and so on. So the model still says that after you see 999 heads, the probability of the next head is just 1/2, because you can compute it's the probability to have 1,000 heads, and this probability to have 999 heads at something. So it's still 1/2. But in the movie, probably you will have different feeling. So why you have this feeling? Why you disagree with the model? Probably you will disagree. And the reason why you think that the head looks more probable is not because in the model it's more probable. It's because you're starting to think that the model doesn't fit the experiment. So there is probability theory and there is statistics. So probability theory somehow studies what are consequences of a given model. And statistics tries to find a good model for experimental data. So there is a kind of separation between them. So in this case, a statistician would say the model of fair coin is not a good model. You should look for a better one, and the better one is just the coin has two heads. I don't remember whether in the movie somebody tried to check, probably not, and this is a bit strange. So statistician will try to find a better model. But if we assume that if we don't touch the model, if we assume this model, in this model we have still the probability 1/2. And now there is a very strange story about an American writer, probably you know him, it's from 19th century. He is famous author of short stories. I think he was one of the first authors of detective stories. And also he is well known for a poem about a raven which always says nevermore, independently of what you ask this raven. Okay, and it seems, at least if we believe, if we take seriously what he writes in one of the stories, it seems that he believed that if you see some probability of 6, if you see 6 already, it decreases the probability to get it another time. Not increases as in our story about coin, but he believed in the opposite direction, and decreases the probability. And what is even more strange, maybe it's kind of mystification, I don't know, maybe just a joke, but in the story it's written quite seriously. I will show you the quote. But it seems that he believed that this decrease is just what probability theory says. And he complained that the general readers, as he said this, do not understand this nice probability theory. So everything was mixed in his explanations. So the correct understanding was considered as something what general readers believe because they are not aware of mathematical theory, and some wrong thing was claimed to be a result of mathematical theory. It looks very strange, but it also reminds a joke about a statistician who computed the probability to have 2 bombs in a plane and decided that the probability is extremely small, it can be ignored. And then he decided that you can bring 1 bomb yourself and then just keep it, and then the probability to have another bomb and to be in danger is extremely small. But of course it's a wrong reasoning, but it's somehow similar to what Mr. Poe thinks. But now I don't want you to believe me, I just want to show you the quote. So this is for the story, detective story. And here is this statement. The fact, if you see already twice the 6, then, says Mr. Poe, it's a reason to believe that third 6 will not appear. So if you see 2 6s, it's a reason to bet against the third 6. Strange. And moreover, he claims that it's difficult to convince the general readers. And indeed, now he explains why the general readers do not believe in this. And they say if you make 2, he says that if you make 2 this dice, 2 6s, they are in the past, so to say. And then you make a new experiment, and why the previous experiment can influence the new one. So this is explained very convincingly. But strangely, Poe believes that this explanation is an error. And of course, if he cannot explain, or I don't know, he doesn't want to explain it, and he just say that, look, the theory says that it's an error, I have no space to explain it. And often when people say things like this, This is just because they cannot explain it. Anyway, everything is mixed here. I don't know what the serious scholar thinks about this. Was it a joke, or did he really believe in this anyway? But I just found this while reading the novel, and it's funny, and so I showed it to you, but I don't know what really this all should mean. Now we came to our goal, so to say, in this part, is the notion of independence. This is a mathematical notion of independence, and this word is used in the normal language in many different ways, and they are not identical with the mathematical notion. I will try to explain. So first, the mathematical definition. A and B are independent if when we use B as a condition, it doesn't change the probability of A. So the conditional probability is equal to unconditional probability. And if we recall the definition of conditional probability as a fraction, this is the fraction, and we can rewrite now like this. And this is symmetric, and this is called the product rule. And the probability of A and B is the product of probability of A and probability of B. But it's actually somehow misleading because it's not a rule, it's a definition. So if this happens, then the event A and B are called mathematically independent. And if it doesn't happen, then it doesn't happen. Nothing bad. So it's not a rule, actually a definition of independence. And for example, if we make, but it's somehow consistent with the language used in some cases. So imagine we have two dice. A is some event about the first dice, I don't know, this X is something, and the B is an event about the second dice, about Y. So then you can check that they are mathematically independent. You know, in terms of our table, we can make a table for X and Y. So events that say about X are just kind of, we select some columns. And event about B, we select some rows. And what is written here, that if we look at the fraction of A inside B, so the fraction of these things inside this, it is of course the same as a fraction of B on these big columns inside the big thing. So everything is proportional. So if two dice are independent in a natural sense, they give also mathematically independent events. Okay. And also, let me say again that there is this strange zero probability case which we can ignore. But if one of the event has probability 0, then of course the end is a part of it, so it also has probability 0. So the formal definition of independence is satisfied, so the impossible event is independent with any other event. It's triviality. And we can look at the bias formula. So if the events are dependent, this means that this probability is not a product. And it can be bigger or smaller. Let's, for example, consider the case when it's bigger. Which means that if we divide this by probability of B, we see that the conditional probability of A given B is bigger. So condition B makes A more probable. And then the symmetry says, this is a symmetric thing. So the symmetry says that the condition A makes B more probable. And this is exactly what we discussed in bias formula. The factor that would change the probability is the same. So the same factor, which how A is increased, how B increased the probability of A, shows how A increased the probability of B. So it's just the bias formula again. So we can clearly see the mathematical notion, and also we should clearly understand that it's not identical to our life, our language and normal life. So in both directions possible. So let's start with a good case we already considered. We have two dice X and Y, two numbers X and Y appearing while rolling a dice twice or two dice, and there are two events. X is a multiple of 2 and Y is a multiple of 3. So they are independent. But now consider different events. Only forget about the second dice. So just event x is a multiple of 2, x is a multiple of 3. And they are also independent. They refer to 1. There is no reason why they should be independent, but in fact they are, because multiple of 2 is 3 numbers, probability is 1/2. Multiple of 3 is 2 numbers, probability is 1/3. And the intersection is 1 number, so it's 1/6. So it fits perfectly well. So there is a mathematical independence. So, but no real life independence, so to say. And another example, when we have a real life independence. So imagine you want to pass an I don't know, some English proficiency test, and you take it once in some organization, and then you want to check the results, and you go to another independent organization which repeats the test. And this organization is independent in the real life sense. But of course, if you just take the statistic, if you look at many people and see whether they passed the first test, the second test, and normally most of the people who pass the first test will pass the second test also, and vice versa. So even the test is independent in the real life, as a mathematical event for a random person taking both tests, they are not independent. And it's explained as correlation. So these tests are correlated, but correlation is not causation. None of them influences the other in any way. And there is a joke about a statistician, a crazy statistician, who decided that visiting a doctor makes you ill, because he just computed the conditional probability of being ill if you visit a doctor, with condition of visiting a doctor. And this probability is bigger than being ill in the general population. Of course, if you look at the people who come to the doctor, then more of them are ill, a bigger fraction of them is ill. So it's true, but you should not. So it's true, but mathematically, but you should not make a conclusion that visiting a doctor makes you ill. And it's actually quite often in the real life. So I don't know. Let's consider some imaginary example. So imagine that you read in the newspaper that, I don't know, drinking coffee increases your lifespan, which means that if you look at the people who drink coffee, then they live longer than an average. But it may well happen. No, I don't claim anything about coffee. Just for example, it may happen just because old people like coffee. So if you so the old people make a significant part of the coffee drinking population. But it's not that doesn't mean that one is the reason of the other one. And still there is a correlation, but not causation, as it's one can say. Again, this take-home message. Now we consider a famous, quite well-known paradox. It's called Monty Hall paradox, or Monty Hall problem, and the name is because of some show of this name when this paradox was appeared. Okay, and I start with a short description, just extracted from Wikipedia. There is a picture. You see this picture, and you see the short description here. And the story is like this. So there is a show, and the player which comes to this show sees 3 doors, and he wants to find a car which is behind one of them. And he picks a door, and the game host opens one of the other doors. And, for example, the 3rd door. And there is no car, there is no prize, just a goat, is just to make fun of the participant. So then the host asks the player whether the player wants to keep the guess or change that. So the player is now allowed to rethink and choose not the door 1 but door 2. And the question is whether the player should do this, or what is the best strategy for the player. And to make the game more clear, we should specify the protocol more exactly. And this is very important, as we will see later. I prepared the slide with things in detail. So first, there is a TV show, and there is a host and a guest. And there are 3 identical doors, 1 to 3. And there is a prize behind one of these doors, so forget about goats. And there is a prize, a car, behind one of the doors. And this door is randomly chosen. And the guest makes a guess where the prize is, also randomly. And then the host opens the other door with no prize. So there is one door with a prize and one door chosen by a guest, maybe the same one, but in all cases there is another door which is not chosen by the guest, and also there is no prize there. So the host opens this door, and if there are 2 possibilities, the host chooses the random one. And then the guest is allowed to keep the guess or to change the guess, and then the door is opened and the prize is given or not given depending on the final guess. If the final guess is correct, the player gets the prize. So this is the game setting in full detail, I hope. And now you can think about the question. So what should you do as a guest in this show? Should you keep your guess after the door is opened, or should you change it, or should you make a new random choice, or whatever? And now I'll try to present several arguments in favor of different theories, and I want to present it in a very convincing voice, so you would be convinced, but then the claim is different, so you cannot be really convinced in all of them. But let me try. So why you should keep the guess? What is the argument why you should keep the guess? And the argument is like this. So, opening the other doors, it's always the host opens the door where there is no prize. So opening this door doesn't really doesn't prove anything about the original door. So there is no reason to change the guess, because this new events do not prove anything to you. So you should keep the old guess because there is no significant new information. Or why to make a new random guess among 2 doors? Another recommendation, and this is supporting evidence. So now, after one door is opened, you can have a prize behind this or behind that door. So the best way is as a random event. So the best way you can behave is just to make a random choice and choose the random door between 2, and then you get the car with the probability 1/2. So it's new random guess, it makes things better. So here is the reasoning. So there are 2 doors, you don't know what is the correct one, but you can make a random choice. And finally, the argument why to change the door. And the argument is like this. The first door, if there was no second part, the first door has a prize probability 1/3. And so the second door is just the complement, is the not event which is not, the first door does not have the prize. So the complement has the probability 2/3, because there is a rule saying that the complement of event has a probability 1 minus probability of the event. So it's better probability, you should do this. So which argument is more convincing for you? And let me now try to move you in other direction, explaining why the arguments are not convincing. So in the first argument, here is it. The opening of the door by the host doesn't prove anything. Indeed, it doesn't prove, but it still provides some new information. Even this information is not decisive, it can change the probability. So why should you ignore this? So this is the refutation of this argument. It's valuable information, but even if it's not decisive. For the second argument says that since you don't know where the car is, the only thing you can do is just to take a random door. But actually there are several things which can be contested here. So for example, the idea that if there is some random process, to get the best chances, you should simulate the process. It's just a wrong assumption. Imagine we have a coin which is more often falls head. So it gives head in 70% of cases. And you want to bet against this coin. And the wrong idea is to imitate the coin, is to try to say head in 70% of cases and tail in 30%. And you will win more if you play against this coin and you always say head. Of course, because there are more chances if you say tail in some case, in some trial, then you decrease your chances in this trial. So why do this? So this is why the second argument is bad. And the third argument, then the probability is 1/3, then the complement is probability has 2/3. And it's an error which we discussed, because this probability 1/3 was for the one experiment, for the first experiment, without this opening the door part. And then we changed the experiment. We have a new experiment now. So new probability is just a probability in a new experiment, and we cannot apply the formula for the sum of probabilities, because they were for the events in the same space. Okay, so now I tried my best to say convincingly what are the argument for and the argument against. So where are you now? What do you think about this question, and what is the correct answer? Stop here if you want to think, and we will give the answer later. So we have three convincing arguments, and now we want to explain the correct answer. Or if we are in a postmodern world, it's not politically correct to say what is the correct answer. We should say this is our position about this problem, and other people have different positions. We don't make any claim. But if we want to be serious, I will try to explain a correct answer and also explain why the setting is not, the initial short setting is not good. Okay, so what do we think about this problem? First, the short setting is not, if we just say the short story, then we don't have any, we cannot say what is the best strategy, because the situation is not clear. And in our elaborated setting, the correct solution is the third one. So indeed, changing the door increases the factor, winning chances by a factor of 2. So why is all this? And there is some general advice how to deal with paradoxes in probability theory. You should think about a repetitive experiment. So if there is no repetitive experiment, it is not clear what is this experiment, then the question is not well posed. But if there is a repetitive experiment and you imagine it, things become more clear. So in our case, there is no problem in repetitions. You can make this show every day and can make the random choices every day. And then you should imagine that the guest follow the first strategy, the second strategy, or the third strategy, and look at which percentage of cases the guest will win. So let's look at this. So by assumption, our price is behind the door 1, door 2, and door 3 in 1/3 of all cases. And in each of the third cases, the guest makes independently the guess. And so this guess is correct with probability also 1/3. So this is enough to say that the keep strategy will win in 1/3 of the days. So if a guest always follows the keep strategy, she will win in 1/3 of the days. But in the other third of the days, she will lose. But if she would use the change strategy, then she would win exactly in the other cases. So in fact, these events can be considered as events on the same probability space, because we just have an experiment in one part, for one strategy the experiment, the rest is not important, but still that we have the same setting, and there are cases when keep strategy is good and cases when change strategy is good, and there are complementary cases. So the change strategy is sure to win with probability 2 over 3. And you can also say that the random choice strategy will win in half of the cases, because new random choice will be correct in half of the cases by definition of independent random choice. So now we know the probabilities for all three strategies and see that the third strategy is the best one. And now let me explain why the short setting, as the story below the picture in Wikipedia, is not enough. Why you should not be, here the story, I repeat it. In search of a new car, the player picks a door, say door number 1. The game host then opens one of the other doors, say door number 3, and there is a goat, and then the player has a chance to change the guess and pick door 2 instead of door 1. So this doesn't tell you what is the experiment, what is the repetitive experiment. This tells you only what happened once. And this information is just not enough. So this is a sequence of events in one case. And to see why it's not enough, imagine the host of the show probably in advance knows that has some instructions what to do here. Maybe they are given or whatever. But imagine the instruction is like this. So first you let the guest to make a guess. And if the guess is incorrect, then you open the door immediately and guess, you save the money. And if the first guess is correct, you still want to save the money. You want to somehow to confuse the guest. And so you say, okay, I open this door, and now you can change maybe the guest will change, and then you save your money because the first guess was correct. So imagine that the host follows this protocol. And in this case, it's obvious that if the host suggested to change the door, it's a clear indication that the guess was correct. So you should keep it, of course. In this setting, the keep strategy will win with probability 1 in the cases when it's applicable, and you should always follow it. So you see that this story is consistent with both descriptions, with this one and our original description. So we cannot distinguish between what is happening behind the scene, and the recommendations depend on what is happening. So this short description is not enough to make an informed decision about best strategy.
Hi, I'm Vladimir Podolsky, and today we are going to discuss random variables and their expectations. On the previous week we have studied probability distributions. We have considered events, which are just subsets of outcomes, and their probabilities. Note that an event is a yes or no question. It either happens or not. It is also important to study numerical characteristics of random outcomes. For this we introduce random variables. A random variable is a variable whose value is determined by a random experiment. So we have a probability distribution on some finite set X with k outcomes. Outcomes have probabilities p1 and so on pk. And to define a random variable f, we have to assign a number a sub I to each outcome. And then f has a value a sub I with probability pi. This looks familiar, and indeed we have already seen this before. For example, if we consider an outcome of a dice throw, then we label each face of a dice by a number. And in this case we already have a random variable. To each outcome we assign some number. There are other examples we have seen, and there are other examples in real life. For example, if we toss a coin, then we can assign 0 to heads and 1 to tails. We have done this in the previous lecture. If we consider a random person in the class, then the age of a random person is a random variable. We assign to each outcome some value. In the same way, a grade of a random person in the class is a random variable. There are some other random variables that arise, for example, in some games. For example, sum of outcomes of two dice throws. This is also a random variable. Before we discuss expectations of random variables, we will discuss the notion of average. So, what is an average salary in some country? Okay, this is the total salary of all population divided by the number of employees in this country. So this is the standard notion of average, which is used everywhere. In mathematics, it is called arithmetic mean. Okay, let's consider the following example. We have a student, and he had 3 tests, and he got scores 78, 72, and 87. What is his average score on these tests? Okay, to compute average, we need to do the following. We need to add all the scores and divide by their number. So we have to add 78, 72, and 87, divide by 3. There are 3 tests. So we have 79. Note that in this case we got lucky and the answer is integer. In general, this is not guaranteed. For example, if we reduce instead of 87, we consider 86 there, we will not obtain an integer number. We will have 78 and 2/3. So this is not always the case, but in this case we have an integer number. Let's consider one more example related to the notion of average. Suppose we have a company and there is HR management in this company, and they use the following strategy. They look at everyone's performance and they fire everyone who performs below average. So what will be a result of such a strategy? Okay, this might sound reasonable. If someone works below average, probably the company should fire him. Okay, but note that unless everyone works equally, which is an extremely rare case, it's very rare that 2 persons perform equally if we measure their work by some number. If it doesn't happen, if it is not the case that everyone works equally, then there is always someone who works below average. Average is something in the middle, so someone works better, someone works not that good, and so there is someone below average because average is somewhere in the middle. So if you fire them, then the average performance will grow. We fired people who work below average, so the average will grow. And then we will have new people below average, because if everyone doesn't work equally, then there is someone below average. If we repeat it several times, we will just be left with just one person who was the best employee. But is it good that we have only one person left? Okay, let's move on to problems that are more related to random variables. Suppose we have a dice, and we throw this dice many times, and each time we have some outcome. What is the average outcomes of all of these throws? Okay, can we give a precise answer? No, we cannot, because this is a random variable. If each time we have as a result 6, then the average outcome will be 6. This is quite improbable, but this is possible. If, on the other hand, each time we have 1, then the average will be also 1. This is again improbable, but this is also possible. So there is no possibility to give some precise answer, which will be always the case. But what we can do, we can give an approximation to an average outcome that will be good. It will be a good approximation with high probability. Okay, let's see what we can do. Suppose we throw a dice n times, and n is very large. Then among outcomes, there are approximately n over 6 ones, n over 6 twos, and so on. So each outcome has probability 1 over 6. So in approximately 1 over 6 of all fraction of all cases, we will have 1. In approximately 1 over 6 fraction of all cases, we will have 2, and so on. Then now we are ready to compute the average. We have to sum up all of the results. So we have 1 over 6 times 1. So we have 1 n over 6 times. We have n over 6 times 2, and so on. So we sum all of this up. We can move n outside of the brackets, and then we have 3.5 times n. This is the sum of all results, approximately again. Okay, and now to obtain the average, we have to divide by the number of experiments. We have to divide by n. We threw the dice n times, so we have to divide by n. So the average is approximately 3.5. Okay, and this is called an expected value or an expectation of a dice throw. Let's consider the notion of expectation in the general case. Suppose we have a random variable, and for simplicity of presentation, let's assume that this is a random variable on the probability space of size 4, so there are 4 possible outcomes. The probabilities of our outcomes are denoted by P1, P2, P3, and P4, and the values of the random variable on these outcomes are A1, A2, and A3, and A4. Okay, let's repeat the random experiment many times. So we have these outcomes. Let's run our experiment, and for example, the outcome was this one. Then in the next experiment, the outcome was the first one. Then again the third one. Then the second one. Then the first one. The third one again. The fourth one. So we can run an experiment many times. And in the end, we will obtain some results. So we have repeated the experiment n times, and n is some large number. Okay, how many outcomes do we have in each of these piles, in each of these columns? We cannot say for sure, but we can say approximately, and this approximation will be good with high probability. Since each outcome since each experiment ends up in the first outcome with probability P1, and we run n experiments, so we have approximately P1 times n in the first column. We have P2 times n in the second column, and so on. Okay, let's see what is the average value of our random variable on all of these outcomes. So we have n experiments, and an outcome A sub I happens about P sub I times n times. So this is the number of times, approximately, that A sub I will occur among the results of our experiments. So to compute an average, we have to add up all the results and divide by the number of values. So we have n experiments, so we have n in the denominator. In the numerator, we will have A1 approximately P1 times n times, A2 approximately P2 times n times, and so on. So we add all of these up, we obtain this expression, and note that n cancels out. So as a result, we have the following expression: A1 times P1 plus A2 times P2, and so on. Okay, this value is called the expectation of f, and is denoted by EF. Note that this value doesn't depend on n. We have during the whole argument, we had n as the number of experiments, but in the end, it cancelled out. So this number doesn't depend on n, it depends only on the random variable. And what is this number? This is an approximation to what we would expect as an average outcome if we repeat our experiment many times. The same construction works in the general case. So if now our random variable has k values, a1 and so on ak, and the probabilities are p1 and so on pk, then to compute the expectation we have to multiply ai times pi for all I, and we have to add up the results from 1 to k. This will result in the expectation of our random variable. Why expectations are important? First of all, expectation is a number, so it is a numerical characteristic of a random variable. And this is important and convenient. We can compare numbers, we can add up numbers, we can do a lot of things with expectations. And on the other hand, this is an important characteristic of a random variable. This is the average value, and it reflects important properties of a random variable, and it is very useful. To get more intuition about expectations, let's also discuss geometric interpretation of an expectation of a random variable. Suppose we have a random variable f with 4 values a1, a2, a3, and a4 with probabilities p1, p2, p3, and p4. And its expectation is equal to a1 times p1 plus a2 times p2, and so on. Okay, let's do the following. Let's consider a system of coordinates. And let's consider on a horizontal axis points 0 and 1. And let's consider interval between 0 and 1. Now, recall that the probabilities p1, p2, p3, and p4 add up to 1. The probability should always add up to 1. So, we can do the following. We have an interval from 0 to 1 of length 1. Let's break it into 4 intervals of length p1, p2, p3, and p4 respectively. Now, let's consider the following graph of some function. On the interval p1, the function is equal to a1. On the interval p2, the function is equal to a2. Here is the correspondence to the vertical axis. On the interval p3, the function will be equal to a3. On the interval of length p4, the function will be equal to a4. There is an intuitive correspondence between this function and our random variable f. Just intuitively, let's say that we throw a random point in the interval from 0 to 1. This is not a formal explanation. This is just an intuition, because formally we do not know what it means to throw a point into an interval. But let's intuitively say that we throw a point into an interval from 0 to 1. And all positions of the points are equal, so we do it uniformly. Then, what is the probability to get into the first interval? This probability will be p1. This probability is the fraction that the first interval takes into the large interval from 0 to 1. Since the interval from 0 to 1 is of length 1, then this fraction is just the length of the first interval, so it's p1. So with probability p1, our point will get into the first interval. With probability p2, our point will get into the second interval. With probability p3, it will get in the third interval. And with probability p4, it will get into the last interval. Now, let's look at the value of this function on this random point. In interval p1, this function is equal to a1. So with probability p1, our function will be equal to a1. With probability p2, our function will be equal to a2. With probability p3, our function will be equal to a3. And in the last interval, with probability p4, our function will be equal to a4. So, and this function behaves on this random point, which we throw into this interval, exactly in the same way as our function f. So, we can speculate that this is a graph of our function. Of course, this is just an intuition. This is not a formal argument. But we can think of this picture as a graph of our function. Now, where is the expectation on this graph? And it turns out it has some very specific meaning on this graph. It turns out that the expectation is the area below this graph. It's the area of these sum of areas of these 4 rectangles. And it is easy to see if you look at the definition of the expectation. Note that what is the area of the first rectangle? Its dimensions are p1 and a1. So the area is the product a1 times p1. And this is the first summoned in the expectation. For the second rectangle, its area is p2 times a2. And this is the second summoned in our expectation. And we proceeded in the same way. So the sum of areas of all these rectangles is equal to the expectation of f. So if we think of f as a graph of this function, then the expectation is the area below the graph of this function. Okay, we have discussed expectations, and actually they are used a lot in various fields. For example, they are everywhere in statistics and sociology. If we hear something about average age in some country or life expectancy, these are actually just expectations. These are expected value. We pick a random person and see its age. So this is a random variable, and average age is the expectation of this random variable. So the same with average grades or average evaluations of students. Hi, I'm Vladimir Podolsky, and today we are going to discuss an important property of expectations of random variables, linearity. Suppose there are two random variables over the same probability space, two random variables f and g. Suppose the outcomes of f are a1 and so on ak, and the outcomes of g are b1 and so on bk, and the probabilities of these outcomes are p1 and so on pk respectively. Okay, now let's consider f plus g. And note that it is also a random variable, and again over the same probability space. The outcomes here are a1 plus b1, and so on, ak plus bk, and the probabilities again are p1 and so on pk. Now, can we say something about the expectation of f plus g? F plus g is a new random variable. Can we say about its expectation at least anything? It turns out that yes, we can do it. So it turns out that the following holds. If we have two random variables f and g on the same probability space, then the expectation of f plus g is equal to the expectation of f plus the expectation of g. And this property is almost immediate. The proof is very simple. Indeed, so let's just use the definition of expectation, and let's just write down the expectation of f plus g. If we do it, then we see that it is equal to f1 plus g1 times p1, so the value of the first on the first outcome times the probability of the first outcome, plus and so on, plus fk plus gk times pk. So the value on the last outcome times the probability of the last outcome. Now, we can split this sum into two parts. In the first part, we will include all summands that contain f1 and so on fk, and in the second part, we will include all summands that contain g1 and so on gk. And then the first part will be f1 times p1, plus and so on, plus fk times pk, and the second part will be g1 times p1, plus and so on, plus gk times pk. And now note that just by the definition, if you look at the first part, it is equal to the expectation of f. And the second part is equal to the expectation of g. So we obtained that the expectation of f plus g is equal to the expectation of f plus the expectation of g, which is what we needed to show. Now, linearity is a very useful property. And the idea is that it allows us to compute expectations of more complicated random variables through computation of expectations of more simple random variables. And this helps a lot. Let's see a couple of examples. Suppose let's consider the following problem. We throw two dice. What is the expected value of the sum of two numbers on them? Okay, we can compute it directly. We throw two dice. There are 6 times 6 outcomes, so only 36 possible outcomes. We can just compute expectation directly. Okay, we can even not consider all 36 outcomes. We can just compute the probability of each value of this sum and write the expression for expectation. But this requires some work. This is not hard, but it requires to do something. But we will show, on the other hand, instead, we will use linearity, and we will show the same. So we will compute the expectation almost immediately. We can, instead of this one random variable, the sum of values of two dice, we can consider two random variables on the same probability distribution. The first one is the value, the number on the first dice, and the second random variable is the number on the second dice. So we throw two dice, and the first random variable is the number on the first dice, the second is the number on the second. So now we have two new random variables, and note that we would like to actually compute the expectation of the sum of these random variables. And instead we can compute the expectation of each of them. And it is, first of all, it's very simple to do, and moreover, we have already done this. So we know that the expectation of each of these random variables is 3.5, and thus the expectation of sum of two numbers on two dice is 7. So let's consider one more example. Suppose we toss a coin 5 times in a row, and we are interested in what is the expected number of tails in these 5 tosses. Again, we can compute it directly. From combinatorics, we know that there are 2 to the 5 possible outcomes. There are 2 possibilities for the first coin, 2 for the second one, and so on. So we have 2 times 2 times 2, and so on, 2 multiplied by itself 5 times. So these are 32 outcomes, and we can just list them all and compute the expectation directly by the definition. Okay, we can even do something more smart. We can try all possible values of this random variable, of the number of tails. Possible values are from 0 to 5, and we can compute the probability of each of them. This will require also some use of combinatorics. We will need to compute the number of combinations. So this requires some work in both of these approaches. Instead, we can use linearity and obtain the answer almost immediately. Indeed, let's introduce new random variables. Let phi I, f sub I, be the outcome of the ith coin. So f sub 1 is the outcome of the first coin, f2 is the outcome of the second coin, and so on. These values are equal to 1 if the outcome is tails, and they are equal to 0 if the outcome is heads. Okay, to compute the number of tails, we have to sum up all these random variables. And now we are interested in the expectation. We are interested in the expectation of sum f1 plus f2 plus f3 and so on. So that's what we need to compute. And again, we can use linearity readily, so we can just compute the expectation of each of these random variables and add the results. Okay, so what is the expectation of each of these random variables? The value, the output of this random variable is 0 with probability 1/2, and it is 1 with probability 1/2. So overall, the value of this expectation is equal to 1 over 2. And if we sum this up, then we will have that if we have 5 coin tosses, then the expected number of tails is 2.5. Consider the following problem. There are 28 randomly chosen people, and we are interested in the following pairs, pairs ij, such that the person with number I has a birthday on the same day as the person with number j. And we are interested in the number of such pairs. We would like to show that the expectation of this number is greater than 1. That means that on average we will have at least one pair of people with the same birthday. Okay, let's discuss in more details what are these pairs and what are we computing. If there are 2 people with the same birthday, then they form a pair of people with birthday on the same day. So they contribute 1 to the number of pairs we are interested in. If there are 3 people with the same birthday, they will form 3 pairs, and they will we can, if we have 3 people, then there is a pair of the first one, the second one, and the third one, and a pair of the first one and the third one. So these people will contribute 3 to the number of pairs we are interested in. So that's what we are going to compute. Okay, the problem looks a bit surprising. So there are just 28 people, and we are saying that it is fair to expect, it will be good to expect that there are 2 of them with the birthday on the same day. But we will show that this is indeed the case. Okay, on the other hand, we have to formalize the problem a little bit. So the current statement is not completely formal. We assume for this problem that birthdays are distributed uniformly among all days of the year, and we assume that there are 365 days of the year for simplicity. We will not discuss it, but actually, if the distribution of birthdays among days of the year is not uniform, which is actually the case in the real life, then this expectation we are looking at will only increase. But for simplicity, we consider a uniform distribution among all days. And also, we have to specify that we choose people independently and uniformly. Randomly here means that we just pick random people with random birthdays. Okay, let's proceed to the proof. And of course, we will use the linearity of expectation here to compute, to have a bound on the expectation we are looking at. Let's denote the number of pairs of people with the same birthday, the number we are looking at, by f. This is a random variable. And let's introduce more random variables. Let's enumerate people from 1 to 28. And let's consider a random variable g sub ij. It will be equal to 1 if persons I and j have birthday on the same day, and otherwise it will be equal to 0. And now an important observation. F is equal to the sum of all gij over all unordered pairs of I and j. That's an important observation we will make, and note that this is the observation that will help us to use linearity. We break our complicated random variable f into the sum of more simple random variables. Okay, but let's see why this is true, why f is equal to the sum of all of these random variables. And let's consider an example. It's easier to see an example. Suppose we have 5 people, 1, 2, 3, 4, 5. And let's just list all of the pairs. There are 5 choose 2 pairs, which is 10, and here they are all listed. First we list pairs with, which contain person number 1, then we list pairs that contain person number 2, then we list pairs that contain person number 3 and that wasn't counted before, and there is finally one pair that doesn't contain anyone from among persons 1, 2, and 3. This is a pair 4 and 5. So we have 10 pairs, and suppose the following happens. The first person, the third person has the same birthday, and the fourth and the fifth person have the same birthday. Okay, so then the values of our new random variables are like this. So they are all zeros except 2 cases, except g13 and g45. Okay, note that f in this case is equal to 2. There are 2 pairs of people that have birthday on the same day. And note that on the other hand, the sum of all gij is also equal to 2, because exactly 2 of them are equal to 1 and others are equal to 0. So in this case, it is easy to see that f is equal to the sum of all gij. It is just the number of pairs such that gij is equal to 1. And if we sum up all gij, we will obtain exactly the same number. So that's why we have our property we will use. Okay, now let's get back to the proof. We know now that the expectation of f is by linearity is equal to the expectation, to the sum of all expectations of all gij over all pairs ij. And there are 2 things left. We need to compute these expectations of simple random variables. And second, we need to count how many pairs of I and j do we have. Okay, let's proceed to the first task. Let's compute the expectation of individual gij. And it is very easy to compute, because this value has only 2 outcomes, 1 and 0. And the first outcome happens with probability 1 over 365, and the second one happens with probability 1 minus 365, but it doesn't matter since the value of this outcome is, the second outcome is 0, so it doesn't matter by which number we multiply 0. And the expectation will be 1 over 365. So now, why the probability of value 1 is equal to 1 over 365. We can just compute it directly. How many possible outcomes are there for the birthday of 2 different people? Each of them can have a birthday in one of 365 possible days. If we have a pair of people, then there are 365 times 365 possible outcomes. And note that only 365 outcomes are good. There are only 365 possibilities for them to have a birthday on the same day. We have to pick one day, and then we have to have birthday. Both of them should have birthday on this day. So we divide 365 by 365 squared, and we obtain our probability. So we have computed the expectation of Gij. And now we can proceed to the second part. How many pairs of I and j do we have? So there are 28 people in total, and we are interested in unordered pairs of people. These are combinations, and there are 28. Choose two pairs. This is 28 times 27 divided by 2, which is equal to 378. So there are 378 possible pairs of 28 out of 28 people. Let's briefly recollect why it's 28 choose 2. Here is a short reminder. For the first person, we have 28 options, and there are 28 possible people. Now we would like to have a pair of different people. So for the second person, there are only 27 options left. And finally, we have counted each pair twice. If we have a pair of the first person and the second one, we have counted it twice. First as we pick the first person first, and the second person second. And the second time we picked the second person first and the first person second. So we counted each pair twice, so we have to divide by 2, and here is why the number of pairs is equal to 28 choose 2. Okay, now let's get back to our proof, and finally we have everything we need. We know that the expectation of f is the sum of expectations of Gij for all pairs of I and j. We know the expectation of each Gij, it is equal to 1 over 365, and we know that there are 378 pairs of people. So overall, we have to add up 1 over 365 as many times as there are pairs of people. So overall we have 378 divided by 365, which is greater than 1. That's what we needed to show. So we computed the expectation of our number, and it turned out to be greater than 1. Hi, I'm Vladimir Podolsky, and today we are going to discuss that expectations doesn't tell us everything about random variables. Consider the following game. So there are two players, Alice and Bob, and each of them has an unconventional dice. For Alice's dice contains the following numbers on its faces. It contains number 2 4 times and number 3 2 times. The dice of Bob contains the following numbers. It contains number 1 4 times and number 6 2 times. Okay, now they do the following. Both of them throw their dices, and the one with a large number wins. Okay, and let's see what happens if the players play these games many times. Who will win more often? Okay, so here is a picture. There is Alice and Bob, and these are their numbers. All numbers are equiprobable. And suppose we play this game. Alice throws 2, Bob throws 6. He is somewhat lucky, and Bob wins in this game. Okay, so this is the game, and let's see. Let's see first of all who has a better expected value of a dice throw. It is good to have better expected value because on average, you throw larger number. Let's see the dice of Alice. It has the outcome 2, the probability 2/3, and it has outcome 3, the probability 1/3. So the expectation is here, and the expectation is 7 over 3. Okay, which is slightly more than 2. Now let's proceed to Bob. His dice has 1 with probability 2/3, and he throws 6 with probability 1/3. So here is the expectation, and the expectation is 8/3. So Bob has a better expectation. Bob has a better expected value on his dice. Okay, but who wins more often? So let's see who wins in this game. And note that actually the game is rather simple. The winner depends only on the throw by Bob. It doesn't matter what Alice throws. Note that if Bob throws 1, then he definitely loses. 1 is smaller than all numbers that Alice has. And if Bob throws 6, then he definitely wins, because 6 is greater than all numbers that Alice has. Okay, Bob throws 1 with probability 2/3, so he will lose with probability 2/3. So Bob loses more often, and substantially more often. 2/3 is much less than 1/3, much greater than 1/3. And this is despite greater expected value. So the dice of Bob has better expected value, but Bob loses more often. Let's see why this happens. So what happened? Where the large expectation of Bob's dice went? So what happened? Note that when Bob wins, he wins by far. 6 is much greater than 2 and 3 that Alice can throw. On the other hand, if Bob loses, he loses slightly. 1 is just slightly less than 2 or 3 that Alice has. So here is where the expectation goes. So if Bob loses, which is not very probable, but if Bob wins, this is not very probable, but he will gain more in the expectation than Alice, much more. And if Bob loses, this is probable, but he will get slightly less than Alice. But note that Bob doesn't get any credit for difference between numbers in these games. In this game, he either loses or wins. The difference between numbers doesn't matter. So that's why the expectation is not extremely relevant to this game. Okay, this example shows that the expected value doesn't tell us everything about a random variable. It might be that the expectation of a random variable is better than for the other random variable, but on the other hand, the random variable is worse because of some other properties. Hi, I'm Vladimir Podolsky, and today we are going to discuss Markov's inequality. In this week we have introduced random variables and their expected values. And now we will see how these notions can help us studying probabilities of events that we have discussed in the previous week. Consider the following problem. Suppose there is a lottery and a ticket costs $10. And it is known that 30% of the budget of the lottery goes to prizes. We need to show that the chances to win $500 or more in this lottery is less than 1%. Okay, first of all, we will use proof by contradiction. We will assume that this is not true, that chances are to win $500 or more are at least 0.001. Okay, denote the number of tickets sold by n. And then we can say what is the budget of a lottery. The budget is 10 times n dollars. Now we know how much money the lottery spends on prices. It is 40%, so this is 10 times n times 0.4, which is 4 times n dollars. This is the money that are spent on prices. Now, by our assumption, recall that we argue by contradiction, by our assumption, at least n over 100 tickets, at least 1% of tickets, win at least $500. So, in total, these tickets win at least n over 100 times 500, that is 5 times n dollars. And this is a contradiction. This is more than the total budget on prices in this lottery. The total budget was 4 times n dollars, and we have obtained that only by these tickets with large prizes we have 5 times n dollars. We can win 5 times n dollars in total. So this is a contradiction. So our assumption is wrong, and we have shown that the statement of the problem is true. The chances to win $500 or more is less than 1%. Now we proceed to Markov's inequality. Suppose there is a non-negative random variable f, that is, f obtain only non-negative values. Then for any positive number a, we have the following. The probability that f is greater or equal than a is at most the expectation of f divided by a. This is a useful inequality, and we can use it in the following way. It allows us to bound probabilities, to show that probabilities are not too large, using the expectations. We have discussed how we can compute expectations, so now we can use this to bound some probabilities. Okay, for the proof of this inequality, it is convenient to rewrite it. It is convenient to multiply both sides by a. Note that a is positive, so we can do it. And we will show that a times the probability that f is greater or equal than a is at most the expectation of f. So we need to show this inequality, and for this let us consider the following new random variable, g. It is a random variable on the same probability space, and it is defined in the following way. So consider some outcome, and the value of f on this outcome is ai. Then if ai is at least a, then g is equal to a on this outcome. And if ai is less than a, then g is equal to 0 on this outcome. So g indicates a certain event. G indicates the following. If on some outcome the value of f is at least a, then g is a. Otherwise it is 0. Okay. Note that g is always less or equal than f on each outcome. Since it is always on all outcomes is at most f, then the average value of g is also at most the average value of f. So we have this inequality. The expectation of g is at most the expectation of f. Again, this follows since g is at most f on each possible outcome. Okay, now what is the expectation of g? Note that g has only one non-zero value. If we write the definition of expectation, then we see that the expectation of g is this value multiplied by the sum of probabilities of outcomes for this value of g. Now we have to see what are these outcomes. Note that these outcomes are exactly the outcomes of the following event. F is at least a. G is equal to a if and only if on this outcome f is at least a. So these are outcomes of the event f is at least a. The sum of the probabilities is this, by the definition, the probability of the event f is at least a. So the sum of probabilities of this outcome is just exactly equal to the probability of the event f is at least a. Okay, and so now we know what is the expectation of g. We have to multiply a by the sum of probabilities of these outcomes, and this sum is equal to the probability that f is at least a. So here is the expectation of g. Okay, now let's sum up what we already have. We have that the expectation of g is at most the expectation of f, and on the other hand we have already computed the expectation of g. It is equal to a times the probability that f is at least a. So if we combine this, we see that the expectation of f is at least a times the probability that f is at least a. And this is exactly what we needed to show. And we have shown Markov inequality. So the idea was that we substituted f by a smaller and simpler random variable, and this way we have obtained the bound between expectation and the probability of the event we are interested in. Okay, now let's see, just to get more intuition, let's see geometric interpretation of this inequality. Now, we have this inequality we would like to show. And suppose, for simplicity of the presentation, suppose that f obtains 4 values a1, a2, a3, and a4 with probabilities p1, p2, p3, and p4. Now, again, recall that we can represent f in the system of coordinates. We can split the interval from 0 to 1 into 4 intervals of length p1, p2, p3, and p4. Recall that p1 plus p2 plus p3 plus p4 is exactly 1, so we can split the interval of length 1 into these parts. We can consider the following graph, which corresponds to the function f. If we throw a point, informally speaking, if we throw a point into interval from 0 to 1, then with probability and see the value of the function with this graph in this point, then with probability p1 it will be equal to a1, with probability p2 it will be equal to a2, and so on. This is exactly our random variable f. So here is the graph. Here is how it corresponds to vertical axis, and here is a from the inequality on the top of the slide. And recall that the expectation of f is just the area of the gray region. On the other hand, we can also see a times the probability that f is at least a in this picture. It's the area of the red region. Indeed, f is at least a on 2 outcomes on this picture, on the outcome a1 and on the outcome a3. So the probabilities are p1 and p3. So this product a times times probability of that a is at least a breaks into parts. It's a times p1 plus a times p3, and these are exactly areas of red rectangles. So now just observe, it is just left to observe that the gray region is larger than the red one. So that's the intuition behind, the geometric intuition behind Markov's inequality. Now we will see an application of Markov's inequality. Consider the following situation. Suppose we have a randomized algorithm that uses randomness in some way. Then running time of this algorithm is a random variable. And suppose that on average algorithm runs in time n squared, where n is the size of input, and the algorithm outputs the correct answer always. Now, we are not happy that our algorithm runs in n squared on average, but in some rare cases it might take a long time, and we are not happy about it. For some reason, we would like it to stop after a certain number of steps. And so we would like to construct a new algorithm, again randomized, that always stops in time some constant times n squared. And we are ready to sacrifice something. We are ready to say that, okay, let our new algorithm to make a mistake on a small, with very small probability. For example, with probability 1 over 1,000. So can we do it or not? Okay, it turns out that we can do it, and we will just apply Markov's inequality to this. Okay, let's proceed to the proof. The running time of our algorithm is a random variable that is denoted by f. And we know that on average the algorithm runs in time n squared. This means that the expectation of f is n squared. Now, here is a new algorithm. We run the original algorithm for 1,000 times n squared steps. And then, if it stops, good, we also stop. Our new algorithm stops. But if it doesn't, the original algorithm is not guaranteed to stop after this number of steps. And if it doesn't stop, we stop it and output something. It doesn't matter what. Let's say output 0. It doesn't matter if it makes sense or not. So just output arbitrary output. Okay, now we claim the following. The probability that the original algorithm doesn't stop after 1,000 times n squares steps is at most 1 over 1,000. And this in particular means that our algorithm makes a mistake with probability at most 1 over 1,000. It can make a mistake only if the original algorithm doesn't stop after this number of steps. Okay, why is the claim true? Indeed, note that the probability, our probability is the following. It's probability that f, our random variable, the running time of algorithm, is at least 1,000 times n squared. And by Markov's inequality, recall that f is a non-negative random variable. Its running time of an algorithm can be negative. So this probability is at most the expectation of f divided by this number in the inequality inside of the probability. So it's divided by 1,000 times n squared. We know that the expectation is n squared. So it's n squared divided by 1,000 times n squared. N squared cancel out. And so we have that this probability is at most 1 over 1,000. And that's exactly what we needed to show. So in this week we studied random variables. They are very useful for it. They allow us to study quantitative aspects of randomness. Also, they allow us to use many analytic tools to study probability, to apply more mathematics to study probability. Next, we considered one of the most important characteristics of random variables, their expected values. And they are also very useful, and there are two reasons for that. On one hand, expectation bears a lot of information of a random variable. It tells us a lot about random variable. On the other hand, expectation is a very convenient thing to study. It is a number, and it has very convenient mathematical properties like linearity, which makes it often very easy to compute. Hi, I'm Vladimir Podolsky, and today we are going to discuss a certain dice game. Consider the following situation. You are in some shady neighborhood of some city, and there is a shady person on the corner of the street who offers bypassers to play a game with him. And here is the game. There are several dices with various numbers on their sides. These are not just standard dices with numbers 1, 2, 3, 4, 5, 6. These are dices with some other numbers possibly, and they are different, so lots of various dices. You and the shady person pick one dice each. And then you throw, both of you throw your dices, and whoever has the larger number on his dice wins. And the winner gets $1 from the loser. And the shady person is eager to play this game a lot, so you can repeat the game and so on. Okay. And the only thing that is unclear is that who picks his dice first. Maybe you just would like to pick the same dice, and then what? And for this, the shady person tells you, okay, that to give you an advantage, he would like to give you the opportunity to pick your dice first. So he lets you pick your dice first, and so you can pick the best dice there is. So you can pick the one that you find best. And the shady person will have to pick among other options, no other choice for him. So you are not allowed to pick the same dice. You pick your dice, and then he will have to pick from other options. Okay, and now we start to look strange. So now the game seems to be favorable to you. So you have an advantage, clearly. And why not to spend an evening and to win, not to win all shady person's money? What is the catch here? And note that in our problem there are no catches that are external to our model. let us not forget that we have a math course. So in particular, the dices are fair. Each outcome has probability exactly 1 over 6. Also, no one will hit you on the head from behind during the game, and no one will pick your pocket. And this is a good time for a disclaimer. Note that all of these are not guaranteed to you in real-life games with cameras, so you probably should avoid these games in real life. But in our problem, the shady person is not cheating. The game will be played exactly as we described it. So, now what do we have? The game seems favorable to us, so we have an advantage. And yet, there is the shady person who is eager to play this game with us for a long time, and with many other people as well, and that's his job. So what's wrong with this situation? What is going on? And it turns out that there is a purely mathematical answer to this puzzle. So once we come closer to the shady person, we can see that he has just 3 dices, and here we are. So the first dice has numbers 1, 1, 6, 6, and 8, 8 on its sides. The second dice has numbers 2, 2, 4, 4, 9, 9, and the third dice has numbers 3, 3, 5, 5, 7, 7. So these are just 3 dices, everything is very simple. Okay, so which of the dices should we pick if we play this game? Now, we are educated, we know something now. We know that we should just compare dices between each other, compute probabilities, and see which of the dices is the best. So let's just do it. Let's start, for example, with dice 1 and dice 2. So what should we do? We should consider all possible outcomes and count winning outcomes for both of the dices, for the first dice and for the second one. And we will see which one is better. Okay, so here is the list of all outcomes. There are 6 outcomes of the first dice, and rows of this table correspond to outcomes of the first dice, and there are 6 outcomes of the second dice, and columns correspond to outcomes of the second dice. So the dice that has larger number wins. So we can see from this picture that, okay, so here are winning outcomes for both dices. And we can count that dice 1 has only 16 winning outcomes, and dice 2 has 20 winning outcomes. So dice 2 wins with probability 5 over 9, which is greater than 1/2. If we would like to, if we have to choose, if we are playing with dice 1 against dice 2, we will win in approximately 5 out of 9 games, and if we play this game long enough, we will start winning, we will start gaining some profit. So dice 2 turns out to be better than dice 1, and so if we play a game with dice 2 against dice 1, we will, on the long run, we will start to win. Okay, so now let's compare dice 2 and dice 3, and we will find the best dice. Dice 2 is better than dice 1. If we compare it with dice 3, we will know which one is the best. Okay, again, we have to consider all outcomes, and we have to count winning outcomes for each of both dices. Here is the table again. So now rows correspond to outcomes of dice 2, columns correspond to outcomes of dice 3, and again, the dice that has larger number wins in this in specific outcome. So here are winning outcomes for dice 3 and winning outcomes for dice 2. So dice 2 now has only 16 winning outcomes, and dice 3 has 20 winning outcomes. Again, as in the previous case, something similar happens. Dice 3 wins with probability 5 over 9. So dice 3 is better than dice 2, and overall we have the following. Dice 2 is better than dice 1, dice 3 is better than dice 2, and so clearly dice 3 is better than dice 1, since dice 3 is better than dice 2 is better than dice 1, and so dice 3 should be much better than dice 2. And we are done. We should pick dice 3 to play this game. Or are we? Is everything correct? Recall that we are playing with a shady person, so we should be careful here. So let's just check, just to be sure. Okay, let's compare dice 3 and dice 1. Again, we have to consider all outcomes. Again, we have to count winning outcomes for each of the dices. And here is the table. Now rows correspond to outcomes of dice 3, columns correspond to outcomes of dice 1, and the dice that has a larger number wins in a certain outcome. So here we can see that here are winning outcomes for dice 1 and here are winning outcomes for dice 3. And we can see that there are only 16 winning outcomes for dice 3 and there are 20 winning outcomes for dice 1. And so dice 1 wins with probability 5/9, which is greater than 1/2. So let's summarize what we have. Dice 2 is better than dice 1. Dice 3 is better than dice 2. We have showed both of these. But it turns out that dice 1 is better than dice 3. So we did the calculation in all of 3 cases. So all of this is true. So how is this even possible? What is going on? So what is happening? And here is some explanation. We are used to compare numbers. We do it a lot. We do it in real life constantly. This is a very common thing we do. And we are used that certain properties hold for numbers. For example, here is one of them. If some number A is greater than some number B, and B is greater than C, then A should be greater than C. This is a very common property. In mathematics it is called transitivity. So we are very used to it. We use it constantly. And it translates to real life experience again constantly. So here is Olympic motto, for example, faster, higher, stronger. All of these, in all of these, we are mostly used that transitivity holds. That if someone is faster than someone else, and the second person is faster than the third person, then the first person is faster than the third one. So this is very typical and this is very standard. But note that random variables are not just numbers, they are more complicated. And it is way harder to compare random variables. And even if we find some way to compare them, like in our game, we compare some random variables in a certain way. If we find some way to compare random variables, we are still not guaranteed that properties we are used to are still holding for random variables. And so this is the problem in our puzzle, in our game. For instance, transitivity in our game doesn't hold, and that's what we have shown. Okay, but what does it mean? What our analysis give us for the game with a shady person? What does it tell us? So let's recall what we have. Dice 2 is better than dice 1. Dice 3 is better than dice 2. Dice 1 is better than dice 3. And now note that the shady person who tells you that to give you an advantage, he will allow you to choose your dice first. Actually, in this specific moment, he is gaining an advantage. He is gaining an advantage because you choose your dice first. So let's see how the shady person will play his game. He should play his game this way, and he certainly will, because that's his job. Dice 2 is better than dice 1, dice 3 is better than dice 2, dice 1 is better than dice 3. So if we pick dice 1, the shady person will pick dice 2. And on the long run, he will start winning. If we pick dice 2, the shady person will pick dice 3. And if we pick dice 3, the shady person will just pick dice 2, which is better than dice 3. And that's the whole strategy for the shady person. Okay, so let's review main lessons we have seen in this video. The probability is tricky. We should be very careful when we apply our usual intuition to probability. It is very tricky and very complicated, sometimes very counterintuitive. And one more lesson, we should probably avoid scam games. Hi, I'm Vladimir Podolsky, and in this video we will discuss the project of our course. So in this project you will create a program that plays the following game. You are given a set of dice, and you are going to play a dice game with this set. First, you have to decide who chooses his dice first, you or your opponent. And then you will play a game against an opponent provided by us. So you and your opponent will choose your dices, and then the throws of the chosen dices will be simulated many times. And your goal is to win as many games as possible. So since you can choose whether you pick your dice first or second, so you are choosing the side for which you are playing, you definitely have an advantage in this game. And the key is to pick the right side, of course. So how should one do that? And it turns out that this simple criteria holds. So suppose there is a set of dices given to you, and the player who picks his dice first can always win in the long run, if and only if there is a dice that is better than all other dices. Okay, so to show, let's see why this statement is true. And to show this statement, we need actually to show two things. First, if there is a dice that is better than all others, then the first player wins. But the converse is also guaranteed, so it should be a criteria. If there is no dice that is better than all others, then the first player doesn't win. So we have to show these two statements, and let's show them one by one. Let's consider two situations. The first one is there is the best dice. So here is our set of dices, and there is one that is better than all others. And then we will show that the first player wins, and the strategy is very simple. The first player should just pick the best dice. And then the second player should pick some other dice, and since the dice of the first player is better than all others, it will be better than the dice of the second player. So the first player will win on the long run. Okay, and now the second case. There is no best dice in this set. So we are given a set of dices, and there is no dice that is better than all others. We have seen an example of such set of dices in the previous video. So now what's going on? Since there is no best dice in this set, it means the following. For any dice, there is some other dice that is not worse than it, that doesn't lose for the first one. In the worst case, they will be equal, so they will have probability 1/2 each. And otherwise, for each dice, there will be just dice that is winning against it. So, and now the second player turns out to have a winning strategy. So suppose the first player picks one of the dices, and then the second player will just, so since we know for each dice, and in particular for this red dice, there is another dice that is better than this one, or at least not worse, so the second player will just pick the dice that is not worse than the red one. And that's the whole strategy. So it's also very simple. Okay, so now, how should your program play this game? Okay, we need first to compare all pairs of dices, and we should check whether there is a dice that is better than all others. We will check our criteria. And if there is such a dice, okay, to win as many games as possible, one should pick the dice that is better than all other dices with highest possible probability. So that wins against all other dices with highest possible probability. And if there is no such dice, one should find for each dice the one that is best against it, and then choose the role of the second player. And then once the first player picks his dice, then we choose the dice that is better than the dice of the first player by as large probability as possible.